Hello children, welcome to online classes. Today we will discuss the properties of p block elements and their compounds. The differentiating electron enters the outermost p orbital. The elements belong to p block. Differentiating electron enters outermost p orbital, then element belongs to p block. 13th group elements are boron, aluminum, gallium, indium, thallium, and 14th group elements are carbon, silicon, germanium, tin, and lead. So today we will be discussing important properties of 13th as well as 14th group elements. First, periodic properties. So let us see the properties: atomic size, ionization potential, electronegativity, as well as reducing strength, nothing but SRP values. See the trend down the group. Atomic size has to increase down the group. So it is increasing from boron to aluminium, but gallium has lesser size when compared to aluminium. Remaining two are increasing down the group. So here the element gallium has d electrons in that which cannot screen nuclear charge effectively. Therefore, gallium experiences more nuclear charge. Hence, size of the gallium is less. Similarly, when you are moving from indium to thallium, also we can see very lesser increment of size from indium to thallium. Thallium is also having F electrons in that, and F electrons also cannot screen the nuclear charge. Therefore, thallium has the increment of size is very much less from indium to thallium. So, gallium is having d electrons and thallium is having F electrons which cannot screen nuclear charge. Next property is ionization energy. Ionization energy will be decreasing down the group. Again, you can see the boron to aluminum is decreasing here. Gallium is having slightly again more than that of aluminum. So reason being same here. Gallium is having more nuclear charge. Hence IP value is more for gallium. Again, if you see from indium to thallium, again thallium is having slightly more value when compared to indium. There's once again same reason here. Thallium is having F electrons which cannot screen nuclear charge effectively. So thallium is having more nuclear charge, thereby it is having more ionization potential. When it comes to electronegativity, here, so En values should decrease down the group. They are decreasing from say boron to aluminum. They are decreasing. Again the value down the group, the values are slightly again they increasing here. So from boron to aluminum, the value is decreasing. Again, they are increasing from say gallium to thallium, the values are increasing. We can say this is because of discrepancies in atomic size of these elements. The values are again changing. When it comes to SRP values here, reducing strength is down the group is decreasing because of decreasing in the SRP values. You see, SRP values is very much higher for aluminum, that is higher negative value says strong reducing agent. They are becoming lesser and lesser negative values. So reducing strength is down the group is decreasing because decreasing in the SRP value, decreasing in the negative SRP values. These are the periodic properties. So moving from boron to thallium, the size is increasing progressively due to the addition of new energy levels. The observed atomic radius of gallium is slightly smaller than that of aluminum. Slightly smaller because of d electrons in that. So when you see ionization enthalpy also, it's decreasing down the group due to increase of size. However, again we can see slight change in the case of gallium. Gallium is having slightly more than that of aluminum because of gallium is having more effective nuclear charge. Down the group, electronegativity is decreasing from boron to aluminum. Again we can see it slightly increasing. This is because of we can see some discrepancies in the atomic size of these elements now. When it comes to the oxidation states here, the common oxidation state of the elements is +3 here. However, down the group again we can see +1 becomes more and more stable. That is because of inert pair effect. Implies thallium exhibits a stable +1 state only. So that is reluctance of Ns electrons ns electron pair to participate in chemical bond formation is known as inert pair effect, and that inert pair effect will be increasing down the group, because we have just now seen that thallium is having f electrons which cannot screen the nuclear charge. Thereby, ns electrons of thallium are firmly bound, and thereby ns electrons are not involving in bonding in the case of thallium. So, down the group, inert pair effect will be increasing. So, down the group, we can see thallium exhibits only +1 oxidation state. Then, compounds. Oxides and hydroxides here, we'll see hydrates afterwards. The compounds, oxides as well as hydroxides here. So boron, both oxide as well as hydroxide, both the compounds are acidic in nature. Both the compounds are acidic in nature. Means if you are observing down the group, you can see that basic property is increasing now. So down the group, you can see basic property increases. Basic property increases down the group. So aluminium compounds, both hydroxide as well as oxides, they are amphoteric in nature. Even gallium compounds are also, both of them are amphoteric in nature. Indium oxide, hydroxide, basic in nature, and last thallium compounds are strongly basic in nature. So oxides and hydroxides, their basic property is increasing down the group. The first one being acidic in nature, remaining two are amphoteric in nature, and remaining last two are basic in nature. This is how the basic property changes down the group. Then compounds, that is halides, if you see, the elements are forming mx3 type of halides, we can say. General formula of these halides will be mx3 we have now. And boron halides, they are covalent in nature. They are covalent in nature and they have trigonal planar structure. They are electron deficient in nature, therefore they are Lewis acids. They are electron deficient because they have only 3 bonds. They require 2 more electrons to get stable octet configuration. So they are electron deficient, and then they are acting as Lewis acids. The order of Lewis acidic character will be BF3 will be less than BCl3, less than BBr3, less than Ba3. Implies that BF3 is going to be least acidic in nature. Now, this acidic property can be explained on this acidic, the order can be explained basis of the halogen boron pi bonding, which is also called back bonding there. That is, in BF3 molecule, boron is having empty 2p orbital. In BF3 molecule, we see boron has empty 2p orbital. So here empty, we have a 2p orbital is there. And the fluorine atom is having completely filled 2p orbital is there in the fluorine atom. So fluorine atom is having completely filled 2p orbital. Therefore, fluorine gives electron pair to boron. So fluorine gives one electron pair to boron here, and thereby involves in the pi bond. This bond itself is known as back bonding also. So due to this BF bond, because of this one, the BF bond is getting partial double bond character, and due to this, it can't take electron pair effectively. Hence, Lewis acidic strength is least in the case of BF3 molecule. Such type of bonding is said to be back bonding, or back bonding. Then, so once again here, one of the 2p orbitals of fluorine atom having a lone pair overlaps sideways with empty 2p orbital of boron atom and forms a pi back bonding, also known as back donation. That is, fluorine is having completely filled 2p orbital here and boron has empty orbital. The fluorine is overlapping sideways with the boron and forming a pi bond. Itself is known as back donation. Then compounds of halides here, let us take aluminum halides now. Aluminum halides are existing as dimers and dimeric structure of Al2Cl6. Each aluminum atom accepts a lone pair of electrons from chlorine atom bonded to other aluminum atom. That is to say, if you see the structure, so aluminum, 2 aluminum atoms are there and 3 chlorine atoms. So Cl, chlorine atoms here around aluminum. So AlCl3, these 3 AlCl3 normal covalent bonds here. Now this chlorine donates electron pair to this aluminum. Similarly, this donates electron pair to aluminum. Thereby it is existing as a dimeric structure. The entire 2 units exist together, which is called dimer. And if you are heating the structure to high temperatures, dimer structure exists in vapor state, below a temperature of 473 Kelvin. When you cross the temperature, it dissociates to form trigonal planar monomeric structure. Means Al2Cl6 dimeric form. When you're heating to higher temperature is higher here, should be more than 473 Kelvin, then that exists as AlCl3 simple monomeric units. This is regarding structures of aluminum halides. Then come some important compounds of boron. Boron important compounds are borax, Na2B4O7 10H2O, then orthoboric acid or simply called boric acid, H3BO3, diborane, B2H6 molecule. Let us take the first compound, borax, which is Na2B4O7 10H2O. The borax consists of different bonds here. So let us take the structure of borax. So that is boron. So 4 boron atoms, which are actually tetrahedral structure we have. Between 2 boron atoms, we have an oxygen atom bonded. That is BOB, we can say, oxygen atom bonded here. And between these two also, we have one more oxygen atom present. And we have hydroxyl groups bonded to each boron atom. So OH here, hydroxyl group here. If you see the structure here, some boron atoms are having 4 bonds. Let us take this boron is having 4 bonds. 1, 2, 3, 4 bonds are there. This boron is undergoing sp3 hybridization. If you see this boron atom is having 3 bonds are there. 1, 2, 3 bonds are there. And this boron undergoes only sp2 hybridization. Means some boron atoms are tetrahedrally bonded. Some of them are trigonal structures we have. And then we have here Na2, it is dot. We have similarly 8 water molecules are there outside this structure. So therefore we can say, we can write even the formula as Na2B4O5 OH taken 4 times dot 8H2O. It is also called sodium tetraborate. It is also called sodium, it is called sodium tetraborate, nothing but borax molecule. So some of them are sp3 hybridized boron atoms here. Some of them are sp2 hybridized boron atoms are there. So all boron atoms are not equivalent in borax. It is also known as sodium tetraborate structure. And there are 8 water molecules which are bonded to 2 sodium ions in the structure. The next, importance of borax. It is used in the borax bead test. Borax on heating loses water molecules, swells up. On further heating, it forms a transparent glassy bead. Which is actually basis for the borax bead test. So borax heating, first of all heating, it is losing these 10 water molecules here and forming sodium metaborate. And then it forms sodium tetraborate. It forms sodium tetraborate first. Sodium tetraborate. On further heating, it becomes no sodium metaborate. It becomes sodium metaborate. And it forms boric anhydride. This entire mixture itself is a transparent glassy mass. In the qualitative analysis, it is used to test for detection of some colored ions like copper, nickel, chromium, cobalt, etc. So the basis of the borax bead test is borax upon heating, it loses water molecules, swells up, and on further heating, it forms a transparent glassy bead. This is the main thing to know the presence of the metal ions. Transparent glassy bead. Let us take, for example, suppose when borax is heated with, say, some copper salts, it forms a blue color bead. Suppose you take a copper salt, we are heating with a borax now. When copper salt is heated with the borax here, it forms copper metaborate is being formed. CuBO2 taken twice, it forms copper metaborate. Plus this will be again boric anhydride. This is blue in color. This compound is blue in color now. So blue color indicates the salt is that of copper salt. So different colors indicate presence of different metal ions there. Suppose if you take iron, it forms a green color bead, it forms. So green color bead indicates presence of iron salts in that. So when you take nickel, it forms brown color bead will be brown in color. If you take manganese, the color is going to be pink color we have now. In this way, different colors of the beads indicate different metal ions. So it is used in the qualitative analysis of the metal ions. This is regarding borax bead test. Then orthoboric acid, or simply called boric acid, another compound of boron. It is a white crystalline solid and it is soapy to touch. It is sparingly soluble in water but highly soluble in hot water. And it is prepared from the hydrolysis of borax. Prepared from the hydrolysis of borax. So borax, Na2B4O7, on hydrolysis it forms NaOH plus, it is forming H3BO3, which is a boric acid. So boric acid can be prepared by hydrolysis of borax. And boric acid is a weak monobasic acid. It is not a arrhenious acid. Means it is not a protonic acid, but it is actually as a Lewis acid there. So boric acid plus water, if you see, it forms tetraborate plus water, plus it forms hydronium ion. Let us see the reaction. It is in this way, that is BOH taken thrice, or the boric acid, plus water. Let us write for convenience like this, H plus and OH minus. OH minus giving rise to. This being electron deficient takes electron pair and this changes into BOH taken 4 times. Plus is given as H plus ion there now. So therefore it's donating proton. Proton is given from water molecule. It's basically accepting electron pair. Electron pair acceptor, therefore it is coming under Lewis acid. Therefore it is Lewis acid. It is not giving its proton, hence it is not called protonic acid, So boric acid is a very weaker acid, is basically a Lewis acid, not a protonic acid. Then action of heat on borax. Action of heat on boric acid. On heating boric acid above 100 degrees Celsius, it forms metaboric acid, and further strong heating, that forms finally boric anhydride. So above 100 degrees it forms metaboric acid. Further strong heating, it is going to give us boric anhydride. Let us see the reaction. So orthoboric acid, that is H3BO3, on heating to about 100 degrees Celsius, initially it forms metaboric acid. It forms HbO2, which is called metaboric acid. And the metaboric acid, so HbO2 on further heating, say to about 160 degrees Celsius, should be more than 100 degrees, then it forms tetraboric acid, plus it is H2O. This molecule is called tetraboric acid. Tetraboric acid. And tetraboric acid, that is H2B4O7, tetraboric acid, on further heating, means strong heating, finally you are going to get boric anhydride plus H2O. This is action of heat on boric acid. So boric acid 100 degrees Celsius forms HbO2, which is called metaboric acid. Metaboric acid further heating gives rise to tetraboric acid. Tetraboric acid further heating gives rise to, that is boric anhydride. This is action of heat on boric acid we have. When it comes to structure of boric acid, so boric acid contains trigonal borate units, that is BO3 minus 3. It has trigonal borate units in which boron atom is sp2 hybridized. Trigonal borate units in which boron is sp2 hybridized. It has hydrogen bond in solid state and has a two-dimensional sheet type of structure. In solid state, it is having hydrogen bonds and is having two-dimensional sheet type of structure. So orthoboric acid has a trigonal borate units, that is BO3 minus units are there, and boron is sp2 hybridized. In solid state, it is having hydrogen bonds, it is having two-dimensional sheet type of structure is there for orthoboric acid. When it comes to hydrides, 13th group elements form hydrides of MH3 type of hydrides are there, but boron forms again different type of hydrides. They are collectively called boranes. Boranes are nothing but hydrides of boron. They are classified into two categories. Two series are there, having a formula BnHen plus 4, which is called nidoboranes, and having a formula BnHen plus 6, which is called arcanoboranes. We have so nidoboranes and arcanoboranes are BnHen plus 4, BnHen plus 6 we have. And among all of them, the simplest borane is a diborane molecule. We have simplest borane is diborane. That is BTS simplest of all borane structure. And regarding the preparation of borane molecule, borane is prepared from boron trihalides only. Borane is prepared from boron trihalides. So reduction of boron trihalides will give us diborane molecule. If you see industrial method of preparation, BF3 is reduced using sodium hydride. NaH is a reducing agent. Reduction is forming as BTH6 plus NeF. In laboratory method, BCl3 is used and is reduced by lithium aluminum hydride. It is also a reducing agent. It forms diborane, lithium chloride, and AlCl3. So BCl3 on reduction using lithium aluminum hydride also gives rise to diborane molecule. Finally, that is when a mixture of boron chloride BCl3 and hydrogen is subjected to silent electric discharge, then also diborane is obtained. So when a mixture of BCl3 and H2 is subjected to silent electric discharge, diborane is obtained. So these are the various methods of the preparation of diborane molecule. So diborane is prepared from boron halides, boron trihalides. On reduction, using various reducing agents, we can get diborane molecule. Then comes the properties of diborane molecule. So diborane is a colorless gas, highly toxic gas, which catches fire spontaneously when exposed to air. Catches fire spontaneously when exposed to air. Stability, it is stable at very low temperatures, and when heated between 373 and 575 Kelvin, it changes into number of higher boranes are being obtained here. When you are heating it to between 373 and 575 Kelvin, it changes into number of higher boranes. It burns in oxygen, releasing enormous amount of heat, and hence used as even a rocket fuel also. So on combustion, so B2H6 when burnt in air, means in oxygen, it forms B2O3 plus H2O, and delta H value is very much high here, minus 2165. We have so many kilojoules per mole. We have it is giving large enormous amount of heat is being produced upon heating in air, hence is used as even rocket fuel also. Other properties of diborane. So diborane on hydrolysis, the reaction with water produces boric acid and liberates their H2 gas here. Hydrolysis, it forms boric acid. With halogen acids, means such as HCl, HBr, and so on and so forth, diborane plus HCl gives rise to this molecule is called chlorodiborane. Bu2H5Cl is a chlorodiborane molecule and liberates H2 gas. With alkalis also, it is forming KBO, which is potassium metaborate, it forms and liberates H2 gas. So with halogen acids, that is hydrolysis, it is forming H2 gas is there plus boric acid. Action of halogen acids, it forms their H2 gas here, and then it forms chlorodiborane. Action of alkalis, it forms H2 gas here and forms potassium metaborate. So one common point remember is with water, that is with water molecule, with halogen acids, and with the base, it is forming H2. H2 is a common product in all the three reactions: hydrolysis, action of halogen acid, and the action of alkalis. It produces H2 as one of the product in them. Then comes next other properties of diborane. So action of halogens here. If you take chlorine, because of its high reactivity, the complete molecule breaks down and we are going to get BCl3 and H2 and HCl there. If you take bromine molecule, it is less reactive in nature, so only substitution takes place in borane, and here you are going to get bromo diborane is being produced. So when you are using chlorine gas, chlorine being highly reactive in nature, it breaks down complete molecule and produces boron trichloride. If you are using bromine gas, it will not break down the molecule, only substitution takes place, and finally you are going to get here bromo diborane is being obtained here now. Then the properties further, the reaction with ammonia is one of the important property of diborane. So diborane reacts with ammonia under different conditions to give different type of products. Different conditions to give different type of products. So if you take diborane with excess of ammonia at low temperature, it is giving us an addition product which is called diammoniate of diborane. It is called diammoniate of diborane. At high temperature, the same composition gives rise to B3N3H6, which is called borazole, or is also called as borazine we have. So with excess ammonia, low temperature, it forms diammoniate of diborane. Same composition, high temperature, it forms borazine or borazole. So addition compound on further heating at 473 Kelvin is giving us borazine or borazole. Borazine has a cyclic structure similar to benzene, hence it is called inorganic benzene. So borazine or borazole is called inorganic benzene there. So let us see the structure of the inorganic benzene. So it is similar to benzene molecule. So nitrogen, but we have alternatively boron and then nitrogen atoms are there. So boron here, and then bonds. Alternate we have double bonds are there, like that of benzene structure here. We have double bonds here, these two, and each atom is bonded to hydrogen atom there. So B3N3H6 structure is similar to benzene, hence called inorganic benzene, but this is more reactive when compared to inorganic benzene because polarity exists in the inorganic benzene, not in the organic benzene. Then comes finally the structure of diborane molecule. So boron is undergoing sp3 hybridization there. So boron forms altogether 4 normal bonds are being formed here. And these bonds, which are the middle bonds, if you are seeing electron distribution, so these 4 bonds, that is boron here and boron here, we can see 4 of them are normal bonds here. So BH bonds, which involve completely electron pair, means this BH bond involves complete electron pair here now. When it comes to the other bond which is being formed between boron, hydrogen and then boron, we have only 2 electrons, means H is here, we have only 1 electron here and 1 electron here. Similarly, we have 1 here and then 1 here now. So only 1 electron pair here is binding 3 atoms, boron, hydrogen and then boron. So it is 3-centered, this is called 3-centered BHB. It is called 3-centered electron pair bond. Only 1 electron pair bonds 3 atoms here. This way, this also have this BHB also 3-centered electron pair bond here. So there are 3-centered 2 electron pair. There are 3-centered electron pair bonds. They are 2 in number here. They are also called banana bonds. This bond BHB bond is also called banana bond. It is a 3-centered electron pair bond we have. This is regarding structure of diborane molecule. So hybridization will be sp3 hybridization of the boron here. Bonds, all of them are not equivalent bonds here. Then when it comes to 14th group elements are carbon, silicon, germanium, tin and then lead we have. And general configuration will be NS2, NP2 we have. General configuration will be NS2, NP2. Then comes the properties, periodic properties of these elements here. Atomic size, metallic nature, these are increasing down the group. Melting point, electronegativity and ionization potential values, all the 3 of them are decreasing down the group. So atomic size, metallic nature will increase, melting point, electronegativity and IP values are decreasing down the group. Then coming towards oxidation states, the common state is +4 state, but down the group here +2 state becomes more stable. That is because of the inert pair effect. So common oxidation state will be +4, but down the group +2 becomes more stable because of inert pair effect here. That is, atoms like germanium, tin and lead show +2 state also because of inert pair effect. But inert pair effect always increases down the group, and therefore for lead +2 state compounds are much more stable when compared to +2 state compounds of tin. So for tin, +4 compounds are stable, but for lead plus 2 are stable because of inert pair effect. And however, they form only covalent compounds, whereas where the covalency of the atoms are 4 we have. So common state is plus 4. Down the group, plus 2 becomes more stable because of inert pair effect here, and then lead is having stable plus 2 compounds here, as the tin is having stable plus 4 compounds. So inert pair effect is more for lead when compared to tin, and they are forming covalent compounds here having a covalency of 4. Then coming towards metallic nature and non-metallic nature, the first two elements are non-metals here. Germanium comes under metalloid, remaining two of them are metals. Means down the group we can say metallic nature is increasing. Then comes catenation property. Here. So that is catenation property. It's a tendency to form long chains of identical atoms. If you are observing the bond energies, the extent of catenation is decreasing down the group. Carbon-carbon bond energy is 3, it is equivalent to 384. See, the values are coming down. So 180 here, 167, 155, and no catenation here. Means down the group, the bond energy strength is decreasing. Bond strength is decreasing. Thereby, the extent of catenation is also decreasing down the group. Then comes allotropy. So various allotropic forms here. All elements except lead are exhibiting allotropic forms here. Carbon exhibits diamond, graphite, fullerenes, and coal, charcoal, lamp black, etc. So these three are coming under amorphous forms. First three are coming under crystalline forms here. Silicon has again crystalline form, amorphous forms are there. Germanium has two crystalline forms here. Tin is having alpha tin, beta tin, and gamma tin we have. Lead doesn't exhibit any allotropic form we have. Let us see the importance of the differences of diamond, graphite, and fullerenes. So importance comes only for those three allotropic forms of carbon. Coming towards diamond and then graphite differences we have. So diamond, as all of us know, is a transparent crystal structure and is opaque crystal structure. It's also having crystalline. Graphite is also having crystalline structure only. It's opaque there. And the brilliance is because of higher refractive index in the case of diamond. It's having just a shining property, on the black shining property it has. Coming towards hybridization, in the diamond, carbon undergoes sp3 hybridization. Here the carbon undergoes sp2 hybridization here. So sp3, therefore, the tetrahedral arrangements, a polymer with tetrahedral arrangement of carbon atoms are there. sp2 here, therefore only 3 atoms are bonded to each and every atom and forms hexagonal rings of the carbon atoms, forming sheets of one carbon atom thickness we have. Sheets of only just one carbon atom thickness we have is a tetrahedral arrangement of carbon atoms in this case. Hardest substance, because a very huge polymeric structure here, is a sheet-like very soft structure. One layer can move over the other layer and thereby very much soft in nature. Then conductivity, it's a bad conductor because all electrons are completely used up in bonding. It's a very good conductor because of the presence of one free electron upon each atom. That free electron starts moving throughout the crystal structure. Density is very high because of the compact structure. Density is not that much high here. We can say low density because of not compact structure like diamond here. And thermodynamically speaking, the diamond is less stable because it's having more energy. Thermodynamically, diamond is less stable because of more energy, and thermodynamically, graphite is more stable because graphite has lesser amount of energy. Does not mark on the paper because of a compact tetrahedral structure. When you are placing a graphite on a paper, it marks paper because due to detachment of few layers of hexagonal rings of carbon when rubbed on the paper. So it is marking on the paper, hence used to making pencil leads here. Used very tough material, hence used as a abrasive for cutting of glass and used in the jewelry and used in the pencils, crucibles, electrodes as well as lubricants. Lubricants, because of the very soft structure we have lubricants here, it marks the paper, hence used in the pencils here now. Electrodes, because of the free electrons are there, it's a very good conductor, therefore it is used as electrodes. These are some of the differences between the carbon, that is allotropic forms, diamond and then graphite we have. Excuse me. Then comes the fullerenes. Fullerenes are allotropic forms of carbon having truncated icosahedron structures. Truncated icosahedron structure. So they are named Fullerenes because of American architect Richard Buckminster Fuller. American architect Richard Buckminster Fuller. Fullerenes have hexagonal and pentagonal structures. Fullerenes have hexagonal and pentagonal structures. If we see the football structure, we can understand it is having hexagonal as well as pentagonal rings on football. So the C60 has 20 hexagonal rings, and then we have 12 pentagonal rings. We have C60 contains 20 hexagonal rings and 12 pentagonal rings we have, whereas C70 contains 25 hexagonal rings and then 12 pentagonal rings we have. Implies that pentagonal rings are same in both the structures. Only thing is hexagonal rings are different. In C60 form we have 20 and C70 form we have 25 hexagonal rings. Implies that both the structures are having hexagonal rings as well as the pentagonal rings in them. Then the carbon atoms are sp2 hybridized in this one, but there is no delocalization of electrons because of non-planar structures. When they're having structures like soccer ball, it will be a circular structure, and thereby it's non-planar structure here. Thereby there is no delocalization of electrons. No delocalization of electrons. C60 is having a spherical shape, the soccer ball of diameter 710 pm, whereas C70 is having structure of a rugby ball. A rugby ball is something like ellipsoidal type of structure. It has two diameters as 780 pm and then 690 pm we have. So a rugby ball is something like ellipsoidal structure. It has two diameters 780 and 690. 690 we have. Whereas C60 spherical shape like a soccer ball, it is 710 picometers we have. Fullerenes are not aromatic in nature. There is no delocalization of pi electrons. They are non-aromatic in nature. Therefore, they are giving us addition reactions similar to alkenes we have. Therefore, they give us addition reactions similar to alkenes we have. So, this is regarding fullerenes. Then comes another important feature of 14th group elements. 14th group elements, it is having a semiconducting property, especially silicon as well as germanium. Now, coming towards N-type. It is offered by silicon germanium when it is doped with the 15th group elements like phosphorus and then arsenic. So the n type of semiconductivity, when you are doping silicon and germanium with 15th group elements like arsenic and phosphorus, the free electron left on phosphorus or arsenic move throughout the crystal structure, and this is said to be n type of semiconductivity. So they are having free electrons are there which are moving throughout the structure, hence they are called n type of semiconductivity because negative charge is moving throughout the structure. Now coming towards p type of conductivity, the same thing when silicon and germanium are say doped with 13th group elements like boron and aluminum. Boron or aluminum, 13th group elements like boron or aluminum, the extra positive hole created on boron or aluminum move in one direction and electrons move in the opposite direction. This is called p type of semiconductivity. So when silicon and germanium are doped with 13th group elements like boron or aluminum, the extra positive hole created on boron or aluminum move in one direction, whereas electrons move in opposite direction, and this gives a p type of semiconductivity. Then comes the compounds of 14th group elements. First one, hydrides. 14th group elements show catenating property and form several type of hydrides are there like CH4, SiH4, GH4, SNH4 and PBH4. They are forming hydrides of several type because of catenating property. So carbon can form even more number of hydrides also, where exclusively an organic chemistry there for that. Coming towards oxides of this group, oxides, of the two types of oxides are there. They are monoxides and dioxides we have. So CO, GeO, SNO, PbO are monoxides, and dioxides are carbon dioxide, CO2, SiO2, GeO2, SnO2 and PO2. When it comes to the properties of these compounds, CO is neutral in nature. CO is neutral in nature. GeO, we can say a distinctly acidic molecule you have. It is acidic in nature. And then remaining two molecules, they are coming under amphoteric properties. Remaining two of them are amphoteric in nature. When it comes to dioxides here, the first two of them, they are acidic oxides. First two are acidic oxides here. And remaining molecules, they are coming under amphoteric in nature. Remaining are amphoteric in nature we have. So implies that down the group we can see one point, down the group basic properties increasing. So this is regarding oxides and dioxides in nature. Now the importance of the first three. So if you see carbon monoxide has a triple bond and then it is having a lone pair of electron on carbon. So it can donate electron pair. So basically acts as a Lewis base and very good ligand. Very good ligand in the complex formation. That is, when you take carbon dioxide structure, is a linear molecule. So 2 sigma bonds and then 2 pi bonds are there. When you take silica is a tetrahedral structure. That is a huge polymeric form. Each silicon is bonded to 4 oxygen atoms. Each silicon is bonded to 4 oxygen atoms tetrahedrally. And it goes on again, one more silicon here. It extends and so on and so forth you have. Structure extends. So silica is solid structure. It is having a tetrahedral. All silicon atoms are tetrahedrally bonded to 4 other oxygen atoms. So tetrahedral structure we have. Then comes towards the halides. So they form tetrahalides. Here, and stability decreases with the increase in atomic number of the central atom. Means down the group we can say stability is decreasing there now. And for the same element, if you see, stability decreases with the size of the halogen atom. Means suppose if you take carbon CCl4 and if you take say SiCl4 and say GeCl4. So here down the group stability is increasing because of increasing in the size of the central atom there now. So stability is decreasing, stability decreases down the group. Now when you take a particular atom, say for example CCl4 here and then CBr4 and say Ci4, if you take like this in this way also, the stability of these molecules is gradually decreasing here now. Decreasing order because the size of the halogen atom is increasing. So stability of the molecules down the group decreases. If you take a particular element also it will be decreasing as the size of the halogen atom is increasing there now. Then comes silicates now. Silicates are polymeric solids having SiO4 units, tetrahedral units in that. This is a basic unit. And there are different type of silicates are there like chain silicates, sheet silicates, cyclic silicates and 3-dimensional silicates also. Earth crust mainly contains silicates in that. So if you take silicate unit, it will be tetrahedral unit of silicate unit contains like this. So each one carries a negative charge. So SiO4 minus 4 here. In short, we can represent like this silicate unit, a triangular form, triangular structure. So these are the 3, and there is one more silicon in the middle having an oxygen atom behind that one. So this is silicon here, representing silicon, and remaining are the oxygen atoms here. All 4 oxygen. This is also an oxygen atom here. So 3 are bonded here. So in short, we are representing like this now. Now different type of silicates, it is coming depending upon the number of oxygen atoms shared per each silicate unit. Number of oxygen atoms shared per each silicate unit. Different type of silicates are formed, which are given as chain silicates, sheet silicates, etc. etc. Suppose when you take 2 silicate units, let us take 2 silicate units like this. One silicate unit, one more unit in this way we have. So these 2 are silicate units. If 2 silicate units say are sharing only one oxygen atom, that is said to be pyrosilicates. They are called pyrosilicates here. Means here it comes in this way. Silicon atom tetrahedrally bonded. Here we have one common oxygen atom. One common oxygen we have. So it comes like this. So this is said to be a pyrosilicate. One common oxygen, that common oxygen atom here. Remaining carry negative charge as it is. So If one atom is shared between two units, it is said to be pyrosilicates now. Suppose two are being shared, means the structure comes like this. Two are being shared, it can extend like this also. It can form chain or else ring it can form. So if you see in this way, in the corners it is shared here now. So this one silicate unit is sharing two oxygen atoms. It leads to formation of chain. It can be even cyclic silicate also. Implies depending upon the number of atoms shared per each unit of silicate, different type of silicates can be obtained. Like one is being shared pyro, two are being shared, it can be chain or else can be chain or even ring silicates and so on and so forth we have. Then comes some organosilicon polymers. Silicones are organosilicon synthetic polymers containing SiO Si linkages. SiO Si linkages. They are obtained by hydrolysis followed by condensation of alkyl halosilanes. Hydrolysis followed by condensation of alkyl halosilanes. So alkyl halosilanes. Hydrolysis followed by condensation. Let us take an example of say R2SiCl2. So you can say it is dialkyl dichlorosilane we have. So but this is a molecular hydrolysis, this on hydrolysis. So this on hydrolysis. So these two Cl atoms will become now OH groups. So OH here, silicon, R, OH and R group we have. A diol is being obtained now. So this on condensation phenomena. This must be condensed now. So first of all, they are hydrolyzed and diols are being produced. They are now condensed. So let us take the condensation of the molecule obtained. So here we have OH, that is silicon here, alkyl group here, one more OH here. You have taken one more diol like this. Again silicon here, R and OH. Between these two, it will be losing one water molecule. So bond is nothing but SiO bond is produced. Like SiO bond is being produced. That way it continues. That way you are going to get linear, planar, cyclic polymers. Different type of polymers are produced. They may be linear, cyclic or planars. So silicones are basically consisting of SiO-Si bonds in that. And they are obtained by hydrolysis and condensation of alkyl halosilanes. Hydrolysis and condensation of alkyl halosilanes. Then coming towards properties of silicones. Silicones can be used as high temperature oil baths. And insulating materials, waterproof clothes can be prepared by them. To mix with the paints, lubricants for airplanes. And as silicone rubbers that retain elasticity even at very high temperature. 15th group elements. 15th group elements include nitrogen, phosphorus, arsenic, antimony and bismuth. They are including nitrogen, phosphorus, arsenic, antimony and bismuth. And their general configuration is NS2NP3. The hydrides and oxides of these elements are poisonous in nature. Hence, these elements are called nicogens. The word nicogen, the term nicogen, is derived from ancient Greek word which means choking or suffocating. Because these hydrides are suffocating in nature, these elements are called nicogens. So nicogens are 15th group elements. Their configuration is NS2NP3. They include nitrogen, phosphorus, arsenic, antimony and bismuth. Now anomalous properties of nitrogen. Nitrogen has a small size, high electronegativity, high ionization energy and non-availability of d orbitals. This property is going to be common for all elements. In all groups, the property is common. The first element, always smaller size, high electronegativity, high ionization energy, and non-availability of d orbitals. It exists as diatomic gas with a triple bond between two nitrogen atoms. So nitrogen can form p pi multiple bonds because of small size, and therefore it can form n triple bond. Due to high bond dissociation energy, it is highly stable and is chemically inert now. So triple bond is having more energy and therefore it is chemically inert. But the single NN bond is weaker than single PP bond present. That is, the nitrogen is small in size, so the non-bonding pairs, so when you take nitrogen atom, the two smaller in size now, so when these two form a single bond here, the non-bonding pairs which are present, they come close to each other now, and then they cause repulsions, they undergo repulsions. The repulsive force will decrease the bond strength. So the single NN bond is weaker when compared to single PP bond because of high interelectronic repulsions of non-bonding electrons. When it comes to phosphorus, the atom is larger size. Though it has same number of electrons here, electron density will not be much, thereby repulsive force between the non-bonding pairs of phosphorus will not be much. Hence, it is having a stronger bond when compared to nitrogen. Nitrogen has a unique ability to form p-pi bond. The formation of p-pi bond depends upon the size of the atom. Smaller sized atom can form always multiple bonds with p-pi bonds with itself as well as with the other elements now. And nitrogen cannot show pentavalency as it does not contain d orbitals in that. The other elements can form p-pi d-pi bonds. Others can form p-pi d-pi bonds. Others cannot form p-pi bonds. So the p-pi bond formation depends upon the size. Small sized atoms can form p-pi bonds. And larger sized atoms cannot form p-pi bonds. Then next one. Coming towards hydrides of this group. The general formula of the hydrides is MH3. So they can be like this: NH3, NH3, then PH3, AS, S3, SB, H3, BaH3. They are having general formula of MH3 we have. Let us see the properties of these hydrides now. Stability. Stability decreases down the group. The stability of these hydrides, because all molecules are covalent in nature, it depends upon the strength between the M and H bond. So the strength of this bond depends upon the size of the atom now. The size of the atom is increasing across the group. It is increasing down the group. So thereby the extent of overlapping will be decreasing now. Hence bond strength decreases. Thereby stability of these hydrides decreases down the group. Reducing strength. When the stability is decreasing down the group, they can lose hydrogen much easily now. Thereby reducing strength is increasing now. Basic nature. All have electron pairs. All have electron pairs on them. Therefore, all the molecules are electron pair donors. Implies all are nothing but Lewis bases now. The electron pair donating property depends upon the availability of electron pair on the central atom. As the size of the atom increases here now, availability of the pair gets reduced. Thereby, basic strength decreases down the group. Coming towards boiling points now. Boiling points among covalent molecules depends upon the molar mass. More the molar mass, more the van der Waals forces, more the boiling point. Therefore, we can see BaH3 being higher molar mass having higher boiling point. But when it comes to ammonia is exceptional because ammonia is having hydrogen bonding. Thereby ammonia comes exceptional here now. So highest boiling point is BaH3 and least boiling point is PH3. This is the order of boiling points. Then shapes now. All hydrides have pyramidal shape due to sp3 hybridization of central atom now and presence of the lone pairs of the electrons on it. So only sp3 means it should be having tetrahedral structure. Because of the lone pairs which are present now, it becomes no pyramidal shape now. Coming towards bond angles, Bond angles decrease and reach to 90 degrees due to pure p orbitals involving down the group. Down the group we can see that pure p orbitals are involving for the formation of hydrides, whereas for ammonia nitrogen will be sp3 hybridized. So all hydrides are pyramidal in structure due to the sp3 hybridization and the lone pair of electrons. Bond angles are getting reduced to 90 degrees because down the group pure orbitals start involving in bond formation. So this is the order of bond angles we have. Ammonia bond angle being highest and bismuthine bond angle being the least we have. This is regarding hydrides. Excuse me. All these elements form two types of oxides. Trioxides M2O3 and pentoxides M2O5 we have now. And we know that down the group metallic nature of these elements are increasing, thereby the basic nature of the oxides will be increasing down the group. So first two oxides are acidic in nature, that is both trioxides and pentoxides. First two of them are acidic in nature. Next two of them are amphoteric in nature, and last is basic in nature. That is to say, the metallic properties increasing down the group, thereby the oxides properties changing from acidic to basic. So first two acidic oxide, next two are amphoteric oxides, and then last one is a basic in nature we have. Now let us see the structure of these trioxides and pentoxides now. Let us see the structure of nitrogen oxides. So trioxides and pentoxide structure. Now the trioxide can be taken as it is a structure of NO plus NO2, because structure is N2O3 you have. Trioxide means it can be taken as a mixture of NO and NO2 structure. So that is NO, we have a lone pair here, and then NO2. NO2 is structure of N2O3 molecule now. When you take N2O5 molecular structure, it can be taken as two NO2 units joined together through one oxygen atom now. So two NO2 units are there. So NO2 unit, and then we have one more NO2 unit this side then now. So two NO2 units are there, and bonding through one oxygen atom we have now. We have one oxygen atom between these two. This is structure of N2O5 molecule. So trioxide and then pentoxide we have. When it comes to phosphorus oxides, say a trioxide of phosphorus, which is a P4O6 structure. So phosphorus, then oxygen atoms which are tetrahedral, and again you have phosphorus here, phosphorus here now, and then between these two one more bond is present. Here one more POP bond is there, and here you have one more bond. So altogether we are, and then each phosphorus has one lone pair of electron on that. So basic unit is called a tetrahedral unit we have. It is having POP bonds are there. It contains POP bonds, and each phosphorus is having three bonds. POP bonds are there, three for each phosphorus atom. When you take phosphorus pentoxide, which is a P4O10, so therefore similar structure we have phosphorus, oxygen, and then here also we have phosphorus here, phosphorus atom, phosphorus here now, another POP bond between these two, one more POP here, one POP here now, and each phosphorus has one double bond here now, one double bond here, one double bond here, and one double bond here we have. The structure of P4O10 structure. P4O10 is having P double bond O's are there, and each one is tetrahedrally bonded here, phosphorus atom. Tetrahedral structure here, each corner. So without lone pairs here, only oxygen will be having lone pairs. These are the structures of the oxides of phosphorus and nitrogen. Then halides now. All elements form halides. All are forming halides. Actually, two types of halides are there, trihalides and pentahalides. So all are forming trihalides now. Except BiF3, all other halides are covalent in nature. All others are covalent molecules now. BiF3 is coming under ionic molecule. Rest of them are covalent in nature. All trihalides undergo hydrolysis. That is, all trihalides undergo hydrolysis here. And all trihalides have pyramidal shape. Suppose when you take say PCl3 molecule, a trihalide structure, pyramidal structure we have. So phosphorus and then 3 chlorine atoms here. We have the clear chlorine atoms and we have a lone pair of electron present on that. So molecule comes under pyramidal structure. So here among trihalides also all undergo hydrolysis except NF3 molecule. NF3 is supposed to be more stable. There is a reluctant towards hydrolysis there now. Then when you take phosphorus trichloride, it is obtained by passing dry chlorine gas over heated white phosphorus. So phosphorus, white phosphorus plus Cl2 giving rise to PCl3 you have. So here 6 and then 4. So we are passing dry chlorine gas over heated white phosphorus. It can also be prepared by action of thionyl chloride on white phosphorus. Thionyl chloride is SOCl2. So P4 plus thionyl chloride SOCl2 also gives us PCl3. Other byproducts are SO2 and then S2Cl2 we have. So it is also obtained by the action of thionyl chloride on white phosphorus. So P4 SOCl2 giving rise to PCl3. Byproducts are SO2 and then S2Cl2 we have. Regarding preparation of phosphorus trichlorides. Coming towards the properties now. It's a colorless oily liquid and hydrolyzes presence of moisture. So PCl3 plus water gives rise to H3PO3 phosphorus acid and byproduct is HCl we have now. So during hydrolysis reactions here, the oxidation state will not change. It is +3 here. It remains here also same +3 state we have now. So PCl3 undergoes hydrolysis and forms here H3PO3. In PCl3, it is a phosphorus is sp3 hybridized. It has a pyramidal shape due to lone pair of electrons. The structure already we have seen in the previous slide. That is a phosphorus having 3 bonds and chlorine atoms here. And we have here a lone pair of electron on that. So one lone pair, it becomes pyramidal and sp3 is sp3 hybridized phosphorus we have. Nitrogen does not form pentahalides because of the absence of d orbitals and the maximum covalency of nitrogen is only 4. Pentahalides are more covalent than trihalides. See, pentahalides will be having +5 oxidation state now. According to Fazan's rules here, more charge always leads to more covalent character. So pentahalides having +5 oxidation state here, whereas trihalides have only +3 oxidation state. Hence, +5 state compounds are having more covalent character. Then, regarding pentahalide preparation now, is again obtained by passing dry chlorine gas on white phosphorus. It must be excess of dry chlorine gas then now. So P4 plus Cl2. It should be excess here now. So PCl5, the chlorine should be excess. Then we are going to get PCl5 now. It is also prepared by the action of SO2Cl2 on phosphorus, not SOCl2, SO2Cl2 on phosphorus. So phosphorus plus SO2Cl2 sulfuryl chloride giving rise to, it forms PCl5 and byproduct is SO2 we have. I am not balancing the equations, I am writing main products in these reactions. So phosphorus on action with SO2Cl2 sulfuryl chloride gives rise to PCl5 plus SO2. Then its properties, PCl5 is yellowish white powder and in the moist air it hydrolyzes to POCl3 first and finally it changes into phosphoric acid. So phosphoric acid has plus 5 state here now, oxidation state, and PCl5 has plus 5 state. So during hydrolysis, we can see that the state retains the same. So first of all, it is forming POCl3. So PCl5 with water forms POCl3 first. Again with excess of water, POCl3 changes into H3PO4. So we can say now PCl5 finally becomes now H3PO4. When PCl5 is heated, it sublimes. But heated high temperature and strong heating, it gives PCl3 and Cl2. So PCl5 is a sublimating solid. It sublimes, but heating very strongly, it dissociates to PCl3 and then PCl5 we have. These are the properties of PCl5. Then coming towards structure. In PCl5, the phosphorus is sp3d hybridized. It has a trigonal bipyramid structure in the gaseous form as well as in liquid form. The bond angles are PCl5 are 90, 120, 180. Let us see the structure of the molecule. So hybridization is sp3d hybridization. Structure is trigonal bipyramid structure. Angles are 90, 120, 180 we have now. So the structure of the molecule, that is a trigonal bipyramid structure we have. We have here phosphorus in the middle we have, and these are Cl atoms. Okay, so bond angles 90, that is to say in the planar angles you can take like this. Between these two we have an angle of 90 degrees here now. 120 means these angles are 120 degrees here. 180 means the entire angle between these two will come 180 degrees for us now. The axial bonds are angle 180 degrees we have. This is a case of gas phase. Is having gas phase and liquid phase, we have same structure. In solid state, the molecule exists as PCl4 plus and then it is PCl6 minus we have the solid state. So it is ionic compound in solid state we have. It is existing as PCl4 plus PCl6 minus. PCl46, this will be tetrahedral part. This is going to be octahedral part we have. So in the gaseous phase, it is trigonal bipyramid structure. Solid phase, we have tetrahedral units as well as we have octahedral units are there. Coming towards oxyacids of nitrogen and respective structures now. So what we have to remember in oxyacids of nitrogen now? In all oxyacids of nitrogen, nitrogen has one OH group. It has one OH group and then one doubly bonded oxygen we have. One NOH group and one doubly bonded oxygen we have except for hyponitrous acid. It's only having different structure hyponitrous acid. That is, we have nitrogen, N2 is there, so double bond and we have two OH groups now. So there are two H2, N2, O2. We have a lone pair of electron here. It's also having one more type of structure. So it's having both anti and syn forms are there for hyponitrous acid. Because of double bond here, rotation is not possible. So two different forms are there for, that is H2, N2, O2. Now nitrous acid. So what we have to see is, we have one double bond NO and definitely we have one OH group. So therefore, nitrogen, we have one double bond O is there and then we have one OH group here. Still we have one more lone pair present on that. The structure of nitrous acid, HNO2, that is a HONO we can say or else. Then nitric acid, the same point must be remembered. Each nitrogen is going to have definitely one double bond O is there. We have one OH group is there and then still we have one more oxygen left and that is going to be a coordinate covalent bond with oxygen we have HNO3 molecule. In pernitric acid we have a peroxy bond that is present. Peroxy bond is there. So again we have nitrogen, one double bond is there. We are going to get a peroxy bond, OO bond is there in this one, no peroxy bond and again you have a coordinate covalent with oxygen we have. These are the structures of oxyacids of nitrogen. Then structures of now oxoacids of phosphorus. So here in all the structures, phosphorus is tetrahedrally bonded. Phosphorus is tetrahedrally bonded we have, and each phosphorus contains one P double bond O and at least one POH group is there in that. And depending upon the formula, it can have one pH group also. So phosphorus is tetrahedral in all the structures here. It has one P double bond O and at least it has one POH group now. Let us see the structures. Say phosphorus acid. So phosphorus acid here, P. One double bond O should be there. And we have say one OH group here now. One OH group is there. So with this we have done with two oxygens now. We have one more oxygen that is present. Implies we have there one more OH group is there. And still we have here one more hydrogen present, implies that we have one hydrogen bonded to phosphorus then now. So implies the phosphorus acid is having two OH groups and one hydrogen now. And hydrogen bonded to phosphorus is responsible for reducing property of the molecule. So OH groups are responsible for oxidizing properties. H is responsible for reducing property, and basicity of this acid is only 2 because we have only 2 OH groups for this. Then comes hypophosphorus acid. Again phosphorus, we have one double bond O is there. It must have one OH group here. With this, two oxygens have been used up. We have remaining two hydrogens left, implies we get here two more hydrogens bonded for this. So it is only monobasic in nature. Then comes pyrophosphorus acid now. This can be assumed that by taking two molecules of phosphorus acid, that is to say H3PO3 phosphorus acid, you take two molecules of this and subtract from one H2O from this. Then you are going to get H4P2O5, pyrophosphorus means. So taking two molecules of phosphorus acid, removing one water molecule. So let us see the structure now. So P should have one double bond O. There are two P atoms. Double bond O we have. Each P must definitely have one OH group. One OH group. One OH group is there now. So with this we are left with only one oxygen atom, odd number of oxygen atoms. So these are bonded through the oxygen atoms here. And still we have two hydrogens left here. Therefore here is H and then here you have H here now. So there are only two OH groups for this. It is also dibasic in nature and molecule contains one POP bond. So pyrophosphorus contains one POP bond in that. Next, let us take now phosphoric acid groups. So principle is same again. So we should have phosphorus atom, doubly bonded oxygen atom will be there and OH group here now. Still we have here two more oxygens left and two more hydrogens are there. That implies you are going to get two more hydroxyl groups for this. So implies it is going to be a tribasic in nature. Now pyrophosphoric acid. Again take two phosphoric acid groups and remove one water molecule from them. Now here there are two phosphorus atoms here. So phosphorus and take one double bonded oxygen atom there. It must have definitely one OH group for each one now. And again it's also having odd number of oxygens are there. Therefore is bonded through one oxygen atom. And still we have here two more hydrogens and two more oxygens are there. Implies that both must have two more OH groups then now. So it implies that it is a tetrabasic in nature now. It is also having one POP bond. Metaphosphoric acid. The molecule is taken n times means it exists as a cyclic structure, it's a cyclic form. Let us take for example trimer, taking n is equal to 3. So there must be only 3 phosphorus atoms then, 3 means here. So phosphorus and phosphorus now. Each P has one double bond O. We have here one OH group here. So one double bond O and one OH group here. Again here also one double bond O and we have here one OH group now. And between these phosphorus atoms join with one POP bond. So POP bond and then POP bond we have. This is going to be a cyclic trimeric structure we have. It can have even n is equal to 4, means you can draw tetramer, hexamer, pentamer and so on and so forth we have. So metaphosphoric acid exists as a cyclic structures, not planar forms. With this we have done with the all oxyacids of phosphorus. Then preparation of nitrogen. In the laboratory, nitrogen is prepared by action of ammonium chloride with sodium nitrite. That is to say, ammonium chloride NH4Cl plus sodium nitrite, that is NaNO2. The main compound is N2 gas plus the byproducts are NaCl plus H2 we have. So N2 can be prepared by the action of ammonium chloride on sodium nitrite NaNO2. It is also prepared by thermal decomposition of ammonium dichromate. So ammonium dichromate, that is NH4 taken twice, Cr2O7 dichromate, on strong heating gives rise to N2 plus chromic oxide plus water. So it is also prepared by thermal decomposition of ammonium dichromate. Then comes pure compound. Very pure N2 can be obtained by thermal decomposition of barium or sodium azide. So azide will be N3 minus is called azide now. Azide ion is there. And N minus 3 is called nitride ion. This is nitride ion. Azide ion we have. Now barium azide. So Ba N3 taken twice we have. On strong heating use elements, that is it forms barium plus it forms nitrogen. So very pure N2 can be obtained by thermal decomposition of sodium, or else you can use barium azide. With this we have done the preparations of nitrogen. Then properties of nitrogen. It is a colorless, odorless, tasteless and non-toxic gas. The two stable isotopes 14 and then 15 we have now. And with elements like lithium and magnesium, it can form nitrides. So lithium nitride forms magnesium nitride now. It combines with hydrogen to give ammonia, presence of ion catalyst, and then promoter molybdenum. Nothing but it is a Haber's process we have. It also combines with oxygen at high temperature to form nitric oxide. And liquid N2 is used as a refrigerant to preserve biological material and then food items now. So once again here, so colorless, tasteless, odorless gas we have. Important properties are it combines with hydrogen to form ammonia, that is the Haber's process we have. It also combines with oxygen at high temperature to form nitric oxide, and liquid nitrogen is used as a refrigerant to preserve biological materials and food items. Then comes ammonia preparation. Ammonia is prepared from decay of nitrogenous organic matter. Decay of nitrogenous organic matter in the nature. When it comes to chemical reactions here, any ammonium salt with a caustic soda use ammonia gas. Let us take common ammonium salt, ammonium chloride plus calcium hydroxide, giving rise to liberation of ammonia gas plus calcium chloride and H2O we have. So any ammonium salt with caustic soda or calcium hydroxide uses ammonia gas. Then coming towards commercial preparation, on large scale ammonia is prepared by Haber's process. As per Lee chart test principle, the favorable conditions for the preparation of ammonia are given to us. Low temperature is maintained, but you are maintaining an optimum value of 700 to 750 Kelvin. High pressure 200 atmospheres is maintained. Catalyst is divided ion we have, and promoter is molybdenum or oxides of potassium and aluminium. So ammonia is done by large scale by Haber's process. So we need to remember all conditions: low temperature, high pressure, catalyst and promoter. Temperatures are 700 to 750 Kelvin, 200 atmospheres we have, and catalyst is finely divided ion, and promoter is molybdenum or else oxides of potassium and then aluminium. Then properties. Ammonia is a colorless and with a pungent smell gas. Colorless gas with pungent smell, and the freezing point is 198.4 Kelvin and boiling point is 239.7 Kelvin we have. It has a higher boiling point when compared to pH3. That is because ammonia is having intermolecular hydrogen bond. So ammonia is a colorless pungent smell gas. It is having higher boiling point when compared to PS3 because it is having intermolecular hydrogen bond. Ammonia is a Lewis base and very good ligand and forms complexes with the compounds of metal ions. So for example, if you take copper ions, say for example like copper sulfate, it reacts with ammonia and forms a complex. It forms Cu NH3 taken 4 times. It's a deep blue in color. This complex is deep blue color we have now. So it forms a complexing agent. So ammonia is an electron pair donor. Suppose when you take silver halide, solid substance, with ammonia, silver ion also forms a complex here. Ag NH3 taken twice it forms, plus and Cl minus it forms. This is completely soluble one. A soluble complex is being formed. Silver diamine chloride is being formed here now. In that way, ammonia forms a complexes, a very good complexing agent we have now. Then comes brown ring test now. Brown ring test for a nitrate salt, freshly prepared ferrous sulfate solution is taken. So for nitrate salt means we take a test tube, it should be in a slanting position. We take a test tube like this. And here a salt solution is taken, means nitrate salt should be taken there now, having a nitrate ion. And then they will be adding freshly prepared ferrous sulfate solution. We have a ferrous sulfate solution here now. So that is a FeSO4 solution is added. And then along the walls of the test tube, they are going to add sulfuric acid now. They will be adding sulfuric acid. At the junction of these two layers, we can see brown color now. Junction we can see some brown color formation, brown layer can be seen. So freshly prepared ferrous sulfate is added to nitrate salt. Then H2SO4 along the walls of the test tube is being added there. We can see a brown ring at junction of two layers. So that is to say nitrate salt is being added to ferrous sulfate solution. And nitrate salt gets reduced to NO there now. And then it forms nitrosoferrous sulfate. This itself is brown color. Nitrosoferrous sulfate is the formula of the complex here. This is a brown in color. Then phosphorus. Phosphorus has 3 allotropic forms. There are white phosphorus, red phosphorus and black phosphorus. White, red and black we have. Now the white phosphorus has individual discrete tetrahedral units and a P4 structure. That is, we can take like this tetrahedral unit. So atoms are 4, another unit. So all of them are individual discrete units present with a bond angle of 60 degrees now. Because of this bond angle 60 degrees, the molecule is having bond angle strain and therefore white phosphorus is highly reactive in nature. When it comes to red phosphorus, it is having a polymeric P4 units are present in that. Means, let us take one unit like this, one more unit, one more, and so on and so forth we have here. Say taken n times will come. In each corner we have a phosphorus atom that is present here. Like this we have. The polymeric structure now. Say taken n times. It's a polymeric form. Because of polymeric structure, the red phosphorus is less reactive in nature. When it comes to black phosphorus, is having a highly polymeric structure when compared to even red phosphorus also. So thermodynamically it is even more stable when compared to red phosphorus. Then comes phosphine gas. Phosphine gas is prepared by the action of calcium phosphide on water or else with dilute HCl. So calcium phosphide Ca3P2 plus, let us take HCl, giving rise to calcium chloride plus PH3, phosphine gas now. But when compared to phosphine and ammonia, these two gases both are hydrides of same group elements only. Ammonia is a very good complexing agent, whereas phosphine is not a good complexing agent. There's a basic difference between ammonia and phosphine. Now, let us discuss the properties of 16th group elements and their compounds. 16th group includes oxygen, sulfur, selenium, tellurium, polonium. These elements are found in ores and minerals. So, the elements of the group are called chalcogens. Chalcogens stands for ore forming elements are called chalcogens. So, for example, hematite ore, Fe2O3, pyrolusite ore, MnO2, zinc blend, ZnS, CuFeS2 and barium sulfide. All are the ore forming, all are the ores. So, these are all ore forming elements, hence they are called chalcogens. Let us take general properties of 16th group elements. The oxygen is the second most electronegative element in the periodic table. The first one is fluorine and second element is oxygen we have. Fluorine, that is electronegativity is 4 units we have, and oxygen electronegativity is equal to 3.5 units. Second element, second most electronegative element. Due to the small size of the oxygen, it has a lower electron gain enthalpy when compared to sulfur. Now here the important point to remember is first electron gain enthalpy of sulfur is more than that of oxygen. Means oxygen being small size has more electron density. It repels the incoming electron more. Thereby oxygen is having less electron gain enthalpy. That is a first electron gain enthalpy. When you are going to the second electron gain enthalpy, oxygen is having more when compared to sulfur now, because O minus ion requires more amount of energy to add one more electron. Hence it requires more energy. So therefore, first electron gain enthalpy, sulfur is more than oxygen. Second electron gain enthalpy, oxygen is more than sulfur. These are the important properties in general characters of these elements. Then coming towards oxidation states, these elements exhibit -2, +2, +4, +6 oxidation states. And due to high electronegativity of oxygen, it always shows the states of -2, except with the fluorine. In fluorine compounds, it exhibits positive oxidation states. Say in OF2, it is having +2 state, O2F2 it is having say +1 state. Except in fluorine compounds, oxygen always exhibits a negative oxidation states now. And oxidation state of oxygen peroxides is -1. So these are all exceptions. So normally it exhibits only -2 oxidation state, and in fluorine compounds it shows positive states, and in peroxides it shows -1 oxidation state. Remaining elements sulfur, selenium, tellurium usually show +4, +6 oxidation states in their compounds now. So remaining, that is sulfur, selenium, tellurium normally show +4 and then +6 oxidation states now. This is regarding oxidation states of these elements. Then comes atomicity, number of atoms in the molecule now. Atomicity of sulfur is 8. So there is S8. It both in rhombic sulfur as well as monoclinic sulfur, it is octatomic molecule only. It is having crown shape, that is to say it comes like this crown shape molecule. So it will be crown shape. So atoms here. So like a crown shape molecule, and the higher temperature, the crown shape, that is S8 rings, start breaking and exists as S6, S4 rings also. S6 rings will be having say chair form, that is the structure comes like this, having chair form, and S4 will be tetrahedral structures we have. So S8 will be crown structure, S6 will be a chair form now. At very high temperatures, normally more than it is 1000 Kelvin, it exists as S2 molecule. Like you can take oxygen molecule, means it will be in this form, which is similar to oxygen molecule. So atomicity of sulfur is 8. It has basically crown shaped structure. At higher temperatures, it starts breaking down into S6, S4 forms. S8 crown structure, S6 is having chair conformation. Very high temperature, it molecule further breaks down and exists as Es2, which is something like oxygen molecule. Then anomalous behavior of oxygen. Oxygen has some anomalous behavior when compared to the rest of the elements in the same group now. This is due to small size and high electronegativity. So oxygen is having smaller size and high En values. Because of these two, it has a different properties. Due to the small size and high electronegativity of oxygen, strong hydrogen bonds are present in water, which is not found in other hydrides of the same group now. So because of high electronegativity, so hydrogen bonds are present in water, whereas hydrogen bond is absent in other hydrides of same group. And oxygen doesn't have d orbitals, hence it limits its covalency to 4. In practice, the valency of the oxygen is rarely it exceeds 2. So normally it restricts its covalency because of the absence of d orbitals. So because of smaller size, high electronegativity, it is forming very strong hydrogen bonds here in water. Others are not having hydrogen bonds. And because of the absence of d orbitals here, it can't expand the octet configuration further. Next comes hydrides of these elements now. So the properties of the hydrides. First point is regarding thermal stability. It always decreases down the group. Thermal stability depends upon the bond strength. Since all molecules are covalent in nature, in covalent molecules, thermal stability depends upon the extent of overlapping. So here we have general formula. Suppose you take it as say H2M, something like say H2O and so on and so forth here. So it depends upon the bond strength between M and then H there now. So it depends upon the extent of overlapping between the orbitals here now. And extent of overlapping here depends upon the size of the central atom here now. When size of the central atom is increasing, extent of overlapping gets reduced. Thereby bond strength gets reduced. That implies stability starts decreasing now. So in the case of covalent molecules, we need to see the stability means here the strength of the bond, and that depends upon extent of overlapping, and that extent of overlapping will be decreasing down the group, and thereby stability decreases down the group. Reducing properties increasing now. When the stability is decreasing, they can very easily give hydrogen, and thereby reducing property starts increasing there. Now acidic character. These compounds, say except water, are having acidic property. Suppose when you take water, say H2O plus H2S if you take now, H2S gives proton to H2O now. Implies it exists as H3O plus and then it is SH minus we have. So it's a proton donor, nothing but an acid molecule. This proton donating property will be increasing down the group. So acidic strength is increasing down the group because of the bond strength is decreasing down the group. The order of boiling points of these hydrates. Boiling points of covalent molecules will depend upon the van der Waals forces. In turn, they depend upon the molar mass. Higher molar mass is going to have always higher van der Waals forces. Thereby, boiling point is going to be higher. But exception is water molecule here, because water molecule is having stronger hydrogen bonding. Other than water molecule, remaining will follow a general trend, we can say. Means higher the molar mass, higher the boiling points. Exception is water is having highest among them because of hydrogen bonding. So the water has higher boiling point than rest of the hydrides and exists as liquid at room temperature because of intermolecular hydrogen bonding that is present. Intermolecular hydrogen bonding is there in water. These are the properties of the hydrides. Thermal stability is decreasing because of decreasing in the bond strength. Reducing property increases because bond breaks very much easily. Acidic strength is also increasing because once again the strength of the bond is decreasing. Boiling points are basically depending upon the van der Waals forces, in turn depending upon the molar mass. Only exception is water because of its hydrogen bond. These are the properties of hydrides. Then comes oxides. So they form two types of oxides here, dioxides and trioxides. We can take it as MO2 and then MO3 type of oxides we have. The acidic strength, if you take dioxides, SO2, SeO2, TeO2, and trioxides SO3, SeO3, TeO3 we have. Whenever oxidation state is same, the acidic strength depends upon the electronegativity. Highly electronegative element is going to be forming a stronger acidic oxide. So thereby SO2 is a stronger acidic oxide. Similarly in trioxides also we see the same trend is being formed. But when you compare acidic strength of say trioxides and dioxides here now, trioxides are having more acidic strength, means we can say SO3 is having more acidic strength when compared to SO2 we have. So when comparing these two, trioxides are more acidic nature when compared to dioxides. Then the first one, sulfur dioxide molecule. So sulfur dioxide is formed by burning sulfur in air. So simple equation, S plus O2 on burning gives rise to SO2 here. Roasting of sulfide ores also gives sulfur dioxide as a byproduct. Suppose when you take zinc sulfide, so roasting in oxygen, that is excess of air now, then we get zinc oxide plus byproduct as sulfur dioxide. So roasting of sulfide ores also gives rise to sulfur dioxide gas now. Then in the laboratory it is prepared by treating sulfide salts with dilute sulfuric acid. Sulfide salts are taken, means you can take an example of sodium sulfide salt Na2SO3 with sulfuric acid, say H2SO4, giving rise to, it forms Na2SO4 plus sulfur dioxide plus it forms H2O. So sulfur dioxide is formed by the action of sulfuric acid on sulfide salts in the lab. Let us take now the properties of sulfur dioxide. Sulfur dioxide is colorless and pungent smelling gas. The smell of burning sulfur. It dissolves in water to form sulfurous acid. That is, SO2 dissolves in water. It gives rise to H2SO3. It forms sulfurous acid. And it reacts with NaOH, forms a sodium sulfite. So when you take sulfur dioxide, say dissolving in sodium hydroxide, it forms there Na2SO3. Sodium sulfite is being formed here. So you can take it as acid and base type of reaction. So that is SO2, acidic oxide, NaOH, basic in nature. It forms sodium sulfite salt. Next, it reacts with the chlorine to form addition compound, which is known as sulfuryl chloride, SO2Cl2. Simple addition reaction only, that is SO2 plus Cl2, it gives rise to SO2Cl2. We have sulfuryl chloride. And when come to the moist sulfur dioxide, behaves as a bleaching agent as well as reducing agent also. And one property is the bleaching action of sulfur dioxide is because of reduction. Bleaching property is because of reduction. It is acting as a reducing agent also. Now coming to a structure. Structure of sulfur dioxide is having a bend shape, and sulfur is undergoing sp2 hybridization and bond angle is 119 degrees we have. So sulfur, we have two double bonds, oxygen atom, a lone pair upon this we have, and sulfur is undergoing sp2 hybridization and bond angles are here 119 degrees we have now. So bend shape and sp2 hybridized molecule. Then halides and respective structures of the compounds here now. Halides and the structures. So 16th group elements form four types of halides: MX6 hexahalides, MX4 tetrahalides, MX2 dihalides, and MX, but they are existing as dimers, that is a monohalides of M2X2 type we have now. Coming to the structures of these molecules here, to find out the hybridization, we require total number of bond pairs plus total number of lone pairs are required now. The total number of bond pairs and lone pairs will give us hybridization. Let us take for example MX6 now. So M is being 16th group element, has a 6 electrons here. It is forming 6 bonds altogether. It implies that MX6 has completely 6 bond pairs are there. 6 bond pairs means hybridization will be sp3d2. Total number of pairs will give us hybridization. Totally we have 6 bond pairs are there. So hybridization is equal to here sp3d2. Let us take an example, say SF6 molecule in that way. So SF6, so structure sp3d2 hybridization, sulfur in the middle, all corners are occupied by fluorine atoms. So if you take SF6 molecule now, it comes in this way. So structure is octahedral structure. Octahedral structure. And it is sulfur is undergoing here sp3d2 hybridization we have. This comes number of bond pairs plus lone. There are no lone pairs here. All of them are bond pairs only. Now let us take MX4. Right? MX4, the central atom, let us take for example SF4 molecule. SF4 molecule. Sulfur is having 6 valence electrons here. So let us take 1, 2, 3, 4, 5 and 6 valence electrons. There are 4 bonds towards 4 halogens. Let us take these are the 4 bonds here. 4 bonds are being formed. And still we have one more lone pair. So number of bond pairs are 4 here. 1, 2, 3, 4 and one lone pair we have now. So total number of pairs, lone pairs plus bond pairs is equal to 5 we have. If it is 5, hybridization is going to be sp3d hybridization. So total number of pairs will decide hybridization. Total number of pairs, if they are 6 in number, that is going to be sp3d2. If they are equal to say 5, that is going to be sp3d we have. If there are total number of 4s are pair, it is going to be sp3 and so on and so forth. Total number of pairs will decide hybridization. In this case, we have 4 bond pairs are there and 1 lone pair we have. So 5, it comes to sp3d hybridization. Let us see the structure now. So the basic form, that is sp3d structure, comes like this. And a lone pair is present in the equatorial plane here. Let us take remaining, all of them are fluorine atoms like this. So here we have a sulfur atom present in the middle. So this structure, so sp3d hybridization is coming at a seesaw structure. It is a seesaw structure we have. One lone pair on equatorial plane, remaining are the bond pairs we have now. So total number of pairs are 5. So it's coming under sp3d hybridization. Let us now take MX2 structure. In MX2 structure here, suppose sulfur is having again 6 valence electrons here, of which 2 of them are bonded here now. So let us take metal M here now, element M, 6 electrons. So 1, 2, 3, 4, 5 and 6. These 2 are forming bond with halogen now. Implies number of bond pairs are 2, number of lone pairs are again 2. Total number of pairs are coming to 4 in this case. Total number of pairs are 4 means it is sp3 hybridization. So molecule is bend shape, means we have metal M and X and X here you have and 2 lone pairs are there. Something like we can say SO, something like H2O structure. So bend shaped molecule we have. And M2X2 type of structure. It is similar to that of H2O2 structure. Structure is like you can take H2O2, which is open book structure. Along the spine of the book, we have the 2 elements which are present here. Means if we take the spine of the book, say metal element here now, and here we have X and X. These 2 are in the 2 leaves of the book. Now if we expand this structure, we can take a structure coming like this. So something like open book structure of say H2O2 structure, that is oxygen atoms in the spine of the book and leaves contains 2 hydrogen atoms. So something like similar to that of H2O2 structure we have. These are the structures of halides now. Excuse me. Then oxyacids of sulfur. Sulfur has many number of oxyacids in which it is sp3 hybridized, and in all oxyacids basicity is 2. Basicity is 2 means all structures definitely have 2 OH groups in that. So 2 OH groups are there in all molecules. Now there are 4 series of acids here. So sulfurous acid series, sulfuric acid series, thionic acid series and peroxyacid series we have. There are 4 series of acids. But in all acids, sulfur is sp3 hybridized here, and basicity is 2 means we have definitely 2 OH groups are there. And at least sulfur is having 1 double bond O will be there, and at least it definitely each sulfur has two OH groups in that. There are two OH groups, and then we have one S double bond O. Minimum S double bond O is there. Basing on this, we can work out the structures of these molecules now. Let us take one by one. Sulfurous acid series now. So basic sulfurous acid means H2SO3, the first molecule, H2SO3. So sulfur dibasic, so definitely it must have two OH groups. All acids have two OH groups there, and sulfur at least has one double bond O. It's nothing but H2SO3 form, sulfurous acid. Now comes thiosulfurous acid. If you are replacing one oxygen say by one sulfur, those compounds are called thiosulfurous acid, thio compounds. Let us take the same structure here. You are replacing this oxygen by sulfur here, and so this molecule is called now thiosulfurous acid. So H2, it will be S2, and then O2 we have. We have replaced one oxygen by one sulfur. H2S2O, it is thiosulfurous acid we have. Then pyrosulfurous acid. The compound pyro means we need to take 2 units of sulfurous acid and remove one water molecule from them. Then you are going to get pyroacids now. We are taking 2 units of sulfurous acids and remove one water molecule from them. It is having here pyrosulfurous acid is going to have 2 sulfur atoms in that. So let us write 2 sulfur atoms in that. And E is dibasic acid, so it should be totally it must have 2 OH groups in that, and each is having one double bond O here now. And since molecule is H2S2O5, we have one more oxygen present, that is going to be double bond O here now. This structure of pyrosulfurous acid. So pyro acids can be assumed that they are obtained by a removal of one water molecule from 2 units of sulfurous acids. Then comes dithionous acid. Dithionous acids. Dithionous acids means they have a group called sulfinic group. Sulfinic group. Sulfinic group is SO2H group. SO2H groups are called sulfinic group. Sulfonic is SO3H. Sulfinic is SO2H. If 2 sulfinic groups are bonded to each other, that is said to be dithionous acid. Dithionous acid. So here, so there are once again double bond O, each sulfur has one OH group, now. So molecule is here H2, it is S2 we have, H2S2 and then O4, which is called dithionous acid. So dithionous acid has sulfur bonding, and there are 2 sulfinic groups. Sulfinic group is SO2H group is there. So these 4 are coming under sulfurous acids now. So sulfurous acids are the basic sulfurous acid, then comes thiosulfurous acid, then comes pyrosulfurous acid, then comes dithionous acid. Then sulfuric acid series we have. The basic compound is sulfuric acid, that is H2SO4 we have. So again there are 2 OH groups because all of them are dibasic in nature. We have 2 more oxygens left, 2 double bond O we have. That is a sulfuric acid structure. Thiosulfuric acid. Again replace one of the oxygen by sulfur. Implies that it should be H2S2O3. You are replacing one oxygen by sulfur. So therefore in structure also just replace one of the oxygens by sulfur. And you are going to get thiosulfuric acid. Then pyrosulfuric acid we have. So again it can be assumed that from 2 units of sulfuric acid, remove one water molecule, you are going to get pyrosulfuric acid. It is also known as by other name oleum, that is H2S2O7. One more name is oleum for this one now. Oleum. Excuse me. Now again one double bond O must be there, each sulfur atom. There must be definitely 2 OH groups altogether we have now, and we are still left with oxygen atoms. So it's having odd number of oxygen atoms, so one comes in between these two then now. So H2S2O7 oleum structure is this. Oleum is actually supposed to be a mixture of sulfuric acid plus sulfur dioxide. So H2SO4 plus SO3 oleum structure. Then comes thionic acid series now. Thionic acid series contain sulfonic groups. That is, they have SO3 H groups are there, which are bonded through sulfur atoms. Sulfonic acid groups bonded through sulfur atoms there now. Let us take the simple one, say dithionic acid. Means we have two sulfonic groups. So this is SO3H group, sulfonic group. One more sulfonic group we have. Both are bonded to each other. This is called dithionic acid. So formula comes out V. It is H2S2. Oxygens are 1, 2, 3, 4, 5, 6 we have. 5, 6 we have. Now when you take trithionic acid, it must have one more sulfur atom now. We have two sulfurs here. One more sulfur comes in between now. Means remaining structures same. So we have like this. One sulfonic group here. We have here one more sulfonic group. Add a sulfur atom between these two. That is called now trithionic acid then now. If it is a tetrathionic acid, add two more sulfur atoms there now. So suppose we have tetrathionic acid. The structure comes here. One double bond over here. Sulfonic, sulfur and sulfur, and then here one more sulfonic group we have. This is called tetrathionic acid. So thionic acid, thionic groups or sulfonic groups or SO3H groups, they are bonded through sulfur atoms. If they are directly bonded, it is called dithionic. One sulfur atom between them, tri, two, tetra, and so on and so forth we have. So we can take the formula as H2, say S2 plus N here, and O will be 6 we have. This N is 0 in this case we have. N is 1 here we have. N is 2 in this case we have. That way we can get thionic acid series now. Then comes finally peroxo acid series. Peroxo series will have peroxy bonds which are present in them. So peroxy bonds are there in that. And peroxy monosulfuric acid means it has only one sulfonic group is there, and then we have one peroxy bond in that. So one sulfonic group SO3H. So SO3H we have. It must have one peroxy bond also. So OH now. It is called peroxo monosulfuric acid. It is H2SO5. One more name is Carose acid. It is also called Carose acid now. So this is the peroxy bond present in that. Peroxo disulfuric acid means it must be having two sulfonic groups, but it has only one peroxy bond as in the case of Carose acid. So two sulfonic groups, SO3H groups here, one peroxy bond here, one more sulfonic group we have. This is H2S2O8 we have. One more name is Marshall acid. This is called Marshall acid now. So H2S2O8 is Marshall acid. It's a peroxy acid series because we have a peroxy bond in that. So sulfur finally forms four types of acid series we have. That is, let us see. Four series are sulfurous acid series, sulfuric series, thionic series, and peroxy acid series we have. Next one, coming towards ozone. Preparation of ozone, that is O3. When a slow, dry stream of oxygen is passed through silent electrical discharge, we can get ozonized oxygen is being formed. So O2 passing through, subjected to silent electric discharge, we get O3. And thermodynamically, O3 is not stable with respect to oxygen. That is reason behind is whenever O3 decomposes, so O3 say giving rise to say O2, it will be 2 and 3 here now. This is going to be definitely exothermic in nature. So this one delta H is going to be negative for this one now. So the process delta H is negative and delta S value will be positive for this one now. Because number of moles are increasing, delta H is positive for this. These two results, that is delta H negative, delta S positive, will make a large negative value for delta G. They will make a large negative value for delta G, and thereby reaction progresses towards the dissociation of O3 molecule. Hence, we say that O3 is thermodynamically less stable when compared to that of oxygen molecule. Then comes properties. Pure ozone is a pale blue color gas and dark blue liquid we have and violet black solid we have. So gas molecule, pale blue, liquid state, dark blue, solid state, violet black we have. And the concentration of ozone rises above 100 ppm, then it becomes difficult to breathe. It becomes difficult to breathe. So then coming towards, it's a very good oxidizing agent because of liberation of nascent oxygen. O3 easily gives rise to O2 plus oxygen. Because of this, it is having oxidizing properties now. Let us see the oxidizing properties of ozone. Some of the oxidizing reactions of ozone. It is oxidizing lead sulfide to lead sulfate. Lead sulfate here. It oxidizes potassium iodide to iodine we have. Potassium iodide to potassium iodine. And then mercury to mercurous oxide. It's actually known as tailing of mercury. Means when you are passing mercury through a glass tube, when you are passing ozone through a glass tube containing mercury, what happens is mercury loses meniscus and touches the walls of the glass tube. It touches the walls of the glass tube because of the formation of mercurous oxide. The phenomena itself is called tailing of mercury. The phenomena is called tailing of mercury. Means losing the meniscus and touching the walls is called tailing of mercury. And then regarding depletion of the ozone layer. So this NO is released by Z planes and directly it acts upon the ozone and forms O2, NO2 plus O2 here now. So means it is one of the reasons for the NO is the reason for the depletion of ozone layer. Then the coming towards structure. The molecule is angular one, bond angle is 117 we have. Bond lengths are equal because of the resonating structures. We can take the structures like this. So oxygen molecule and one of them is going to be coordinate bond here now. And then another structure, it will be the other way. So coordinate bond here and then double bond here you can take. So resonating structures of these two and thereby bond lengths are equal and both are equal to 1.28 angstrom units and bond angle is 117 degrees we have. And it is used as germicide, disinfectant, bleaching agent and oxidizing agent. If you see these three properties, disinfectant, bleaching agent and oxidizing agent, all three are because it is liberating nascent oxygen. Very good oxidizing agent. So because of the nascent oxygen only, is having these three properties which are disinfectant, bleaching and oxidizing properties now. Then comes sulfuric acid preparation, its properties now. Sulfuric acid is one of the most industrial chemical used worldwide and is manufactured by contact process. The principles used in the contact process is burning of sulfur or sulfide ores to generate first of all sulfur dioxide gas, and SO2 is further oxidized to SO3 here, and SO3 is absorbed in H2SO4 to form oleum. That's to say SO3 plus H2SO4 gives rise to H2S2O7, oleum is being formed. And once you get oleum there, means H2S2O7, when you add water for this, on distillation you are going to get back the sulfuric acid molecules. So oleum is dissolved to get, SO3 is dissolved to get oleum there. Oleum is hydrolyzed to get back the sulfuric acid. This is all the sulfuric acid prepared by contact process. Then properties, the colorless, dense, oily liquid is having stronger hydrogen bonds in that and specific density of 1.84. Dissolves in water with evolution of large amount of heat now. So it's highly exothermic in nature, dissolution in the water. Hence, the concentrated acid must be added slowly to water to prepare dilute acid now. So we cannot add water to acid. We need to add acid to water very much slowly to prepare the dilute sulfuric acid. Then comes the acid is having strong dehydrating property and it has more affinity towards water molecules there now. It charges the carbohydrates and forms black residue because of its dehydrating property only. Suppose when you take C12 say H22O11. You have taken carbohydrate there. And then presence of sulfuric acid. It should be the concentrated one. It absorbs water molecules completely. It absorbs here 11 H2O molecules, and finally carbon is left off. So we can see a residue of carbon form. It charts the carbohydrates. And then hot and then concentrated sulfuric acid is moderately strong oxidizing agent. So moderately strong oxidizing agent. So it both metals and nonmetals are oxidized. Metals as well as nonmetals are oxidized by this. So let us take copper plus sulfuric acid, giving rise to, it forms copper sulfate and then sulfur dioxide plus water we have. If we take carbon, carbon also gets oxidized to corresponding carbon dioxide, and H2SO4 becomes sulfur dioxide plus water. Means both metals as well as nonmetals can be oxidized by this. Now let us discuss properties of 17th group elements and their compounds. 17th group includes fluorine, chlorine, bromine, iodine and acetine. These elements are born from sea salts with most of the metals. So they are called halogens. The word halogens is of two words, halus and gen. Halus stands from sea salt, gen stands from born. So they are born from sea salts, hence called halogens. The general configuration of these elements, halogens, is Ns2Np5. They have 7 electrons in the outermost orbit. Let us take the general properties of these elements. Atomic radii and ionic radii increases down the group. It's a general trend. And here, these are small sized atoms in their respective period because of higher nuclear charge. But still down the group, atomic size will be increasing. Ionization enthalpies, because of more nuclear charge, they are having higher IP values. And once again, IP values decrease down the group. Electronegativity, they are highly electronegative elements in the periodic table, and the order of En values, fluorine being the highest in complete periodic table. So fluorine, then more than chlorine, then bromine, then iodine, and all the values are according to Pauling scale values only. Electron gain enthalpy, being small size, they have a higher electron gain enthalpy, but exception is fluorine. Fluorine is having lesser value than chlorine because fluorine is small size and has high electron density. When you compare fluorine and chlorine here now, so chlorine is a larger sized atom, whereas fluorine is a small sized atom now. So it is having more electron density when compared to chlorine. It's having more electron density, it starts repelling the incoming electron. Thereby, it has a less electron gain enthalpy. So lesser electron gain enthalpy for fluorine, it's because of small size and then higher electron density. Then coming towards physical properties, color, a fluorine yellow colored gas, chlorine green yellowish gas, bromine reddish brown liquid, iodine violet solid. Violet, it can be called a sublimating solid. Iodine is violet sublimating solid. The bond enthalpies decrease down the group due to increase of their size. Again, exception is fluorine. Because in the case of fluorine, being very small size here, to form fluorine molecule, the fluorine atoms come close and they have non-bonding pairs now. So when atoms are coming close to form fluorine molecule, the non-bonding pairs also come close to each other, and they start repelling with each other. So repulsive force present between these two will decrease the bond strength. So exception is fluorine. Fluorine is having lesser value. That is because of small size, non-bonding pairs undergo more repulsions, and repulsive force decreases the bond strength in this. So order of the bond enthalpies are chlorine more than bromine, then comes fluorine, and then iodine we have. Then the oxidizing power is in the order of. So So they are the best oxidizing elements in complete periodic table. Fluorine being the best. Fluorine, then chlorine, then bromine, then iodine we have. So here fluorine is a best oxidizing agent. That is because of its low bond enthalpy as well as higher hydration enthalpy. Fluorine has the highest value because of low bond enthalpy as well as a higher hydration enthalpy. When it comes to oxidation states here, all halogens exhibit -1 oxidation state. And due to high electronegativity and absence of d orbitals, fluorine mainly exhibits -1 state. So fluorine mainly exhibits -1 because of high electronegativity as well as absence of d orbitals. The other elements, chlorine, bromine, iodine, exhibit +1, +3, +5 as well as +7 oxidation states. Now, other elements are going to exhibit positive states, that is a chlorine, bromine, iodine exhibit +1, +3, +5 and then +7 oxidation state. Then comes anomalous behavior of fluorine. The anomalous behavior of fluorine is due to its small size, high electronegativity, low bond dissociation enthalpy and non-availability of d orbitals. So 4 points are there. Anomalous behavior of fluorine is because of small size, high electronegativity, low bond dissociation enthalpy and non-availability of d orbitals. Most of the reactions of fluorine are highly exothermic in nature. Since it is most electronegative element, it cannot combine with oxygen to form oxyacids. So oxyacids are not there for fluorine because it cannot combine with highly electronegative oxygen. Then when it comes to hydrides, hydrides are of formula HX type we have. We can take, that is HF, then comes HCl, then HBr, then HI. So general formula of hydrides is HX. Let us see the stability of these hydrides now. Since all molecules are covalent in nature, the stability depends upon the bond enthalpy. Between H and then X we need to see the bond enthalpy. And bond enthalpy depends upon the size of the central atom now. When the size of the atom is increasing down the group, when size increases down the group, the extent of overlapping of the orbitals between the hydrogen and halogen atom decreases. Due to this, bond enthalpy gets reduced, thereby stability decreases. So decrease in the stability is because of decreasing in the bond enthalpy. Reducing properties increasing down the group. Reducing property increases, that is because when bond enthalpy decreases, bond breaks easily and they can give hydrogen easily now. So thereby they are reducing agents as well as reducing strength will be increasing now. Acidic strength is increasing, that is because when you take HCl molecule and you add water to this one, the proton donor, so it exists as H3O plus here, is a proton for this, and then Cl minus ion. This proton donating property will be increasing down the group because we can say decrease of bond strength. Coming towards boiling points, because all molecules are covalent in nature, the boiling points depends basically upon the molar mass of the compounds now. And molar mass of the compounds are increasing down the group. Thereby boiling points have to increase. The only exception is HF, because HF is having hydrogen bonding, therefore the molecule is having highest boiling point. So HCl will be having least boiling point here. Then next higher is HBr you have now. Next higher is HI, and highest is the HF because of the hydrogen bonding. This is the order of boiling points in that. Then among the hydrides, the important property of HCl is formation of aqua regia. HCl forms aqua regia. And importance of aqua regia is noble metals also can dissolve in aqua regia. And aqua regia is 3 parts of concentrated HCl and 1 part of concentrated HNO3. 3 parts of HCl and 1 part of HNO3. So noble metals also dissolve in aqua regia. Suppose when you take the example of gold, let us take the reactions here. HNO3, that is one part of HNO3, and say 3 parts of HCl will give us NOCl plus Cl, chlorine, free chlorine, highly active in nature, plus H2O. When you are adding gold to the mixture here, it reacts with the free chlorine and forms AuCl3, that is auric chloride. This auric chloride starts dissolving in HCl and forms there HAuCl4. It is a water soluble one. This is completely soluble. So therefore gold will dissolve in the aqua regia because of the formation of HAuCl4. HAuCl4 is also known as tetra 4 chlorines are the tetrachloroauric acid. Similarly, we can write reactions for platinum also. Platinum also dissolves in aqua regia. So aqua regia importance is noble metals also dissolve in aqua regia, and aqua regia is 3 parts of HCl with 1 part of HNO3. Then interhalogen compounds. Halogens combine among themselves to form a number of compounds which are known as interhalogen compounds of type, that is XX dash, XX dash 3, XX dash 5, XX dash 7 we have. So where X the central atom, the larger atom we can say, X dash is a smaller halogen atom we have. Suppose when you take the first category of say XX dash here, ClF, BrF we can take now. ClF, BrF. Coming towards ClF will be something like Cl2 structure, chlorine and then fluorine we have here. So non-bonding pairs. So this is a structure of ClF we have. Then next category, now it is XX-3 we have. Example is say ClF3 molecule. ClF3 molecule is having three bond pairs. 3 bonds are there, 3 bond pairs, and 2 lone pairs are there. So total number of pairs always give us hybridization now. So we have here 3 bonds are there and 2 lone pairs are there. Means altogether 5 pairs are there. 5 pairs stands for sp3d hybridization. So sp3d hybridization, the structure is, so it has basic form, trigonal structure we have. And then let us take ClF3, the Cl is here now. And in the equatorial plane, you have the lone pair of electrons present there now, equatorial plane. Remaining fluorines are there along the axis as well as one along the equatorial plane. Therefore, structure is a T-shaped molecule. So, number of pairs, how to see the number of pairs means here, chlorine is having totally 7 valence electrons. So, 1, 2, 3, 4, 5, 6, 7 we have. And there are 3 atoms fluorine forming bonds. So it will be 1 fluorine bond here, 1 more here, and 1 more here. Means we have here 3 bond pairs are there and 2 lone pairs of left. So therefore it is having 3 bond pairs and 2 lone pairs are there. So total number of pairs are 5. If we have 5 pairs, that will be sp3d hybridization. 6 pairs sp3d2 we have. 6 pairs stands for sp3d2 we have. 4 pairs will stand for sp3 hybridization. That way we can find hybridization and structure. Next category, the molecule is X-5. An example is say BrF5 molecule. Again, when you are trying to find hybridization here now, so Br central atom having altogether 7 electrons here. So 1, 2, 3, 4, 5, 6 and 7 here. There are 5 atoms forming bonds here. So 1, 2, 3, 4 and 5 bonds are there. Implies there are 5 bond pairs are there here altogether. We have only 1 lone pair left. 1 lone pair. Altogether we have 6 pairs are there. No, 6 pairs stands for sp3d2 hybridization. Therefore, structure will be sp3d2 hybridization. That is, there is a 1 lone pair present on that. Lone pair occupies here, lone pair here. Remaining or Here BrFi we are taking here. Let us write the Br here and then fluorine atoms here now. So the base is square and we have a pyramid on this type. So we can take it as a square pyramidal structure, but it will be distorted square pyramid structure because of lone pair of electrons which are present in that. Next one. Next structure is X7. Let us take IF7. So all 7 bonds are there. No lone pairs on that. So there was 7 means it will be sp3, D3 hybridization we have. So it will be structure is going to be octahedral, the pentagonal structure. So pentagon we have, and then the central atom is say iodine here now, and all corners are occupied by fluorine atoms. All are fluorine atoms. So this will be pentagonal bipyramid structure. No lone pairs. All of them are bond pairs. So sp3, D3 hybridization we have. Then comes one of the important point regarding interhalogen compounds. They undergo hydrolysis now. In these reactions here, a small halogen comes out as HX and larger one comes out as oxoacid of that. Let us take for example ClF undergoing hydrolysis giving rise to. Here the smaller one is fluorine, it comes out as HX, that is HF. Larger one is chlorine we have, it comes out as HOCl. So oxidation state will remain same. It is a +1 here per chlorine atom. It also has +1 in this oxyacid now. Suppose when you take ClF3 plus water giving rise to, again smaller one is F, it forms HF plus, larger is chlorine having +3 state here now. It forms an oxyacid where chlorine is having +3 state. It is a HClO2 is having +3 state for this. So all molecules undergo hydrolysis. They form 2 compounds. The smaller one is coming out as HX. The larger one is coming out as corresponding oxoacid of that. With this we have done with interhalogen compounds. Then oxyacids of halogens now. Now oxides of halogens here. All oxyacids of halogen are monobasic in nature. All of them are monobasic. All are monobasic. So all are monobasic means all have only one OH group in that. All have one OH group in that. If you are seeing the structures here, in the structures the chlorine has only one OH group. One single bond OH group is there because all of them are monobasic in nature. And then the chlorine forms double bonds with all other oxygen atoms which are present now. So chlorine forms ClO bonds with all other oxygen atoms present. So in all oxyacids, chlorine has one OH group. Remaining all oxygens form multiple bonds, double bonds with the chlorine atom now. Let us now take the first one, HOCl here now. So OH group, only one OH is there. So it will be Cl and then OH group. Cl and then OH group here. When it comes to in which state it is being formed. Now chlorine, when you take this having NS2NP5 configuration, that is 3s2 3p5 we have. So 3s2, let us take 3s2 3p5. So 3s2, 2 electrons here, and 3p5, 4 and 1 we have. So in ground state, chlorine is having one unpaired electron here. So it can form only one bond. Therefore, hypochlorous acid is formed in the ground state for chlorine. And OCl minus ions are called hypochlorite ions. Hypochlorite ions. Then comes the second one, that is a chlorous acid, HClO2. HClO2, chlorine must be having definitely one OH group is there and one double bond O must be there then now. One double bond O. Then coming towards number of lone pairs which are present on that. We know that chlorine altogether has 7 electrons, of which 1 is used here now. 2 of them are used up here now. 3 are used. Therefore 3, 4, 5, 6 and 7. Implies we have altogether 2 bonds and 2 lone pairs are there. 2 plus 2, 4. 4 pairs are there means it's undergoing sp3 hybridization. And when you take the ground state configuration is, let's say 3s2 So 3s2 we have 3s2, 3p5 we have. So in ground state, it can form only one covalent bond. But here in the molecule we have altogether, there are three covalent bonds are there. So therefore, it must undergo excited state. So one of the p electrons moves towards the d orbital then now. So therefore, the configuration comes out to be, so it will be, now we have three unpaired electrons are present, therefore it forms three covalent bonds as in the case of HClO2. So therefore it forms the molecule in first excited state of chlorine atom. So HClO2 forms in the first excited state of the chlorine atom. Now let us see the structure. So there is one double bond or one OH group we have, and the salts are known as chloride salts. Salts are known as chloride salts. Let us take the next one, that is chloric acid. We have HClO3. So always chlorine has one OH group is there. There are two more oxygens left off here. So there must be two double bonds which are there, and therefore it must be having only one lone pair that is being present. So we have three bonds and one lone pair, means again four are there. Four means it is going to be sp3 hybridization. Because of one lone pair here, that is going to be pyramidal structure. So sp3 and pyramidal structure we have. Let us take in which state it forms. In the previously we have seen in the first excited state we have here three electrons which are present here now. Now let us take that first excited state first. So here we have two electrons are there, two electrons here. So 1, 2, 3. The first state we have only three electrons now. Here it is forming altogether. There are 1, 2, 3, 4, 5 bonds are there. We require two more electrons, means one more electron gets excited here now. It moves here, means finally you are going to get here, that is here one electron, 1, 1, 1 and 1 we have. There are now 5 electrons which are present. It is in the second excited state. It forms a HClO3 now. Now structure is, there are two double bonds, one OH group. We have one lone pair present on this. And the anions are called chlorate anions. Chlorate anions here. Then next one, the last one, perchloric acid, HClO4. So Cl, so we have always one OH group. Remaining all must be doubly bonded oxygen atoms which are present there now. So there it implies that there are no more lone pair of electrons on that. So and base CT is equal to 1. If you see 4 bonds are there, hence 4 pairs implies sp3 hybridization. No lone pairs, therefore it is going to be perfect tetrahedral structure now. If you see the previous form here, previous structure, it is a second state we have now. Let us take the second state once again here. In second state here, we have altogether 5 lone electrons are there. It is forming 5 bonds now. But here you require another 2 more bonds, because 6 bonds are there with oxygen atoms and one OH group here. Send one more to this one here. That is, therefore, all 7 of them are now completely unpaired here. It forms 7 covalent bonds. That is said to be third excited state now. Third excited state we have. So it is a no peroxy bond, though it is called perchloric acid, there is no peroxy bond in this one. So structure is, we have altogether Cl, one OH group is there, remaining all of them are multiple bonds like this. So tetrahedral structure is regarding the oxyacids of chlorine we have. Then comes chlorine preparation properties. First one, prepared from manganese dioxide. So MnO2 with HCl gives rise to MnCl2 plus Cl2 and H2O. So Cl2 can be prepared by the action of HCl on manganese dioxide there. One more reaction is by action of HCl, potassium permanganate also. So KMnO4 plus HCl, this also gives chlorine gas. KCl, MnCl2, Cl2, H2O we have. So action of HCl on manganese dioxide, action of HCl on potassium permanganate, both will give us chlorine gas now. Next, coming towards manufacturing process. It is called, one is called Deacon's process. It is by oxidation of HCl, by atmospheric oxygen, but in the presence of heated CuCl2. The presence of, we are using CuCl2 at a temperature of 273 Kelvin. Is basically acting as a catalyst there. So therefore it will be HCl plus heating in atmospheric oxygen, and we require here CuCl2. Temperature is 723 Kelvin we have. It forms here Cl2 and then H2O. So this will be on balancing, 4 will come here and then 2 moles will come. So oxidation of HCl with atmospheric oxygen in the presence of CuCl2 at a temperature of 723 Kelvin give rise to chlorine gas. One more is the electrolysis of brine also gives chlorine gas at anode. So brine solution NaCl will give rise to Na plus Cl minus ions we have in aqueous solution. So Cl minus ions being anions move towards anode. So therefore at anode Cl minus ions move, oxidation takes place. So liberation of chlorine gas takes place at anode now. At cathode, actually water molecules get reduced at cathode there. So at cathode H2O gets reduced because of the electrons which are given there. It forms H2 and then OH minus ions are being produced here now. So it forms that is liberation of OH minus ions and liberation of H2 gas at cathode. So brine solution upon electrolysis will liberate chlorine gas at anode. Then comes properties of chlorine. It is a greenish yellow gas with pungent and suffocating odor, soluble in water, and it is called chlorine water. Chlorine water on standing for long time loses its yellow color due to formation of HCl and HOCl. So chlorine water contains HOCl in that. And hypochlorous acid gives nascent oxygen responsible for oxidizing and bleaching action of chlorine we have. So when you take HOCl, that is hypochlorous acid which is present in chlorine water, this gives rise to HCl plus nascent oxygen. And this is responsible for bleaching action as well as oxidizing properties of chlorine water. Then reaction with alkalis. So with cold and dilute NaOH, it is forming sodium hypochlorite, that is NaOH plus, if you take chlorine gas, it forms here, it should be dilute and cold conditions. It forms NaCl plus it forms NaOCl plus H2O. This is called sodium hypochlorite. If you take the same chlorine gas NaOH, but NaOH should be in the hot conditions, then it forms chlorate. NaOH plus Cl2 giving rise to, it forms there NaCl plus NaClO3 plus H2O, and this is called chlorate now. And both the reactions are coming under disproportionation reactions only. We can see that the oxidation state of chlorine is increasing as well as decreasing. If you take here 0 state we have, it is becoming here -1 and then +1 in this case we have now, -1 and +1. If you take here becoming -1 and +5 states we have. So both the reactions are examples of disproportionation reactions we have. Then when chlorine reacts with the dry slaked lime, it forms bleaching powder. So a chlorine here plus calcium hydroxide giving rise to, it is forms CaOCl2 dot to H2O. It is nothing but bleaching powder. So with the slaked lime, chlorine gas is giving us bleaching powder. Then reaction of chlorine with ammonia. If you take excess of chlorine with ammonia, we are going to get NCl3, is unstable compound, and HCl it forms. And if you take excess of ammonia, the same chlorine gives rise to ammonium chloride and liberates N2 gas. So excess chlorine gives NCl3, HCl. Excess ammonia, it gives rise to ammonium chloride plus N2 gas. Then coming towards oxidizing properties of chlorine. Chlorine oxidizes ferrous sulfate to ferric sulfate, sulfur dioxide to sulfuric acid, iodine to iodic acid. Let us take the reactions now. If we take ferrous sulfate, say for example, ferrous sulfate FeSO4 in acidic medium, so H2SO4 plus chlorine, this gives rise to Fe2SO4 taken thrice plus HCl you have. So ferrous sulfate becoming ferric sulfate there now. If you take sulfur dioxide and then chlorine, say in water, this forms sulfuric acid now. H2SO4 it forms. Again byproduct is HCl we have. If you take iodine and say chlorine here, iodine and chlorine plus water, this forms here HiO3 iodic acid plus it forms HCl. So in all the cases here Cl2 is becoming now HCl, means is becoming -1 state there now, and others are getting oxidized. These are the oxidizing properties of chlorine molecule. So with this we have come to an end of 17th group elements. Now let us discuss properties of 18th group elements and their compounds. 18th group elements include helium, neon, argon, krypton, xenon and radon. All these are gases, and because of completely filled sublevels, they are chemically unreactive. Hence they are called inert gases or noble gases. They are chemically unreactive because of completely filled sublevels. Therefore they are called inert gases. All the elements except helium have the general outermost configuration Ns2Np6. Helium is having 1s2 configuration. 1% of atmosphere contain noble gases. In that, the order of abundance is argon more than neon, than krypton, than helium, than xenon. So, in atmosphere, 1% is of noble gases, and in that the order of abundance is argon more than neon, then krypton, then helium, then comes xenon. Now the general properties of 18th group elements. Atomic radii increases down the group with increase in atomic number, the general trend in any groups. Ionization energy decreases down the group, but due to stable configuration, they have very high ionization enthalpy values. Because of completely filled sublevels, they have higher IP values, but again down the group IP values will be decreasing now. Since noble gases have stable electronic configuration, they have no tendency to accept electrons, and therefore they have large positive values of electron gain enthalpy. So because of stable configurations, they do not have tendency to accept electrons. Therefore, they have large positive values of electron gain enthalpy. Then the physical properties of these elements. All noble gases are monoatomic in nature. They are colorless, odorless and tasteless gases. They are sparingly soluble in water, and they have very low melting as well as boiling points. Because the only type of interatomic interactions present is weak dispersion forces. They have only very weak van der Waals forces, and helium is having the lowest boiling point, which is 4.2 Kelvin. So all noble gases are monoatomic, colorless, odorless, tasteless gases. They are sparingly soluble in water, but solubility increases down the group. They have very low melting and boiling points. That is because they have very weaker van der Waals forces present between these atoms. And helium is having lowest boiling point, and it is 4.2 Kelvin. Then the xenon fluorine compounds. Xenon fluorine compound, that is xenon fluorides, XeF2, XeF4, XeF6. Now, all these are prepared directly from elements itself, that is xenon and fluorine. But the fluoride formed depends upon three factors. Depends upon the ratio of the elements used, as well as temperature and then pressure. The type of the fluoride formed depends upon the ratio of these elements used, temperature as well as the pressure. Now when you take excess of xenon and fluorine at 1 bar pressure at a temperature of 673 Kelvin, the compound formed is XeF2. If you take the ratio as 1 is to 5 at 7 bar pressure and 873 Kelvin, XeF4 is being formed. The ratio is 1 is to 20, then under 60 bar pressure, means higher pressure, and 573 Kelvin, then compound formed is XeF6. So all these xenon fluorides are prepared from elements xenon and fluorine itself, but the compound form depends upon three factors, depends upon the temperature, pressure and the ratio of the elements which are used. And then xenon XeF6 can also be prepared by interaction between XeF4 and O2F2. XeF6 can also be prepared by interaction of XeF4 and O2F2, which gives XeF6. All xenon fluorides are colorless crystalline solid substances and they are powerful fluorinating agents and are easily hydrolyzed. All compounds are colorless crystalline solids and they are powerful fluorinating agents as well as compounds undergo hydrolysis very easily. So for example, when you take xenon fluoride upon hydrolysis, that forms xenon HF and liberates oxygen gas. Xenon fluoride XeF2 and hydrolysis gives xenon HF and then oxygen gas. Xenon fluorides react with fluoride ion acceptors to form cationic species and fluoride ion donors to form fluoroanions. Suppose when you take PF5, because of availability of vacant d orbitals in this can very easily accept fluoride ion and exists as PF6 minus. So this can be considered to be fluoride ion acceptor now. So when you take reaction between XeF2 and PF5, so PF5 accepts fluoride ion here, it takes F minus here now. Thereby it will be XeF plus is being formed. It is now the cationic species in this. So if you have a fluoride ion acceptor like PF5, SbF5, the xenon fluorides exist as cationic species now. If you have a fluoride ion donors like say metal fluorides, they will become very easily M plus and F minus ion. If we take the reaction between XeF6 and metal fluoride here, XeF6 accepts F minus ion now. It forms anion then now. So with the fluoride ion donors like metal fluorides, they are existing as a fluoroanions then. If we have a fluoride ion acceptors, they are existing as a cationic species. Fluoride ion donors, they are forming fluoroanions. In the shapes of xenon fluorides now. So XeF2 structure. The total number of pairs of electrons which are present around xenon in XeF2 is 5 pairs now. Because if you take xenon here, so 8 electrons, 1, 2, 3, 4, 5, 6, 7, 8 are there. There are 2 bonds, F2 means the 2 bonds are being formed here. So let us take 1 and then 2 here now. So 2 of them are bonded pair of electrons here. Remaining 3 are lone pairs present. Altogether we have 5 pairs of electrons. That is to say 5 pairs are being formed. 5 pairs means it is sp3d hybridization. Total number of pairs, lone pairs plus bond pairs comes up to 5. It is going to be sp3d hybridization. 3 lone pairs and 2 bond pairs are there. And it is formed in first excited state. Let us see how it is formed in the first excited state. Now when you take the ground state configuration, say it's a NS2 NP6 we have. NS2 NP6 in ground state here. So 1, 2, 3, 4. This is the NS2 NP6 state we have. In the ground state, xenon doesn't have any unpaired electrons now, so it cannot form any of the compound. In XeF2 formation here, it requires 2 unpaired electrons to form 2 bonds. So therefore, one of the p electrons must be excited to d sublevel. Means now the configuration will be in this form now. So 1 electron here and 1 in this case you are going to get. So 1 electron goes to the d sublevel. Now this is in the called first excited state we have. This is the first excited state we have. Now there are 2 unpaired electrons here. Hence it can form XeF2 compound. So XeF2 is being formed in the first excited state. So hybridization is sp3d hybridization. There are 3 lone pairs and 2 bond pairs are there. So sp3d hybridization here, there are 3 lone pairs here and 2 bond pairs. So the structure is linear. Then next compound, xenon XeF4 now. Total number of pairs again here now. It is having totally 4 bond pairs and 2 lone pairs are there. 4 bond pairs, 2 lone pairs. Altogether we have 6 pairs. 6 pairs comes under sp3d2 hybridization we have. sp3d2 hybridization now. Let us see the how it is formed in second excited state. In first excited state, we have the configuration like this. So 2 electrons here, 2 here, 2 here, 1 in P, 1 in D we have. It is the first excited state. It is having only 2 unpaired electrons now. We require 4 because it is XeF4. So again one of them must be excited here now. So thereby the new configuration will be like this. So 1 here, 1 here, 1 here and 1 here. Now this is going to be second excited state. This is the second excited state we have. Now we have altogether 4 unpaired electrons, so it can form 4 bonds. So XeF4 forms in the second excited state of xenon. And sp3d2 structure with the 2 lone pairs are there. Therefore the structure comes under square planar form. Square planar form. So total number of pairs will decide hybridization there now. Lone pairs, bond pairs will decide the structure out there. And to get the excited state, we require how many number of bonds are being formed by that central atom. Next, coming towards XeF6 now. Total number of pairs in XeF6 will be, that is 5 plus 1 we have. Altogether, 6 plus 1, 7 pairs are there altogether now. Because 6 bonds are being formed, XeF6, still we have one more lone pair on that. So 7 are there. 7 comes under sp3d3 hybridization. sp3d3 we have. Now it is forming 6 bonds. So we require 6 unpaired electrons present on that. So if you have seen the previous structure, we have seen it is a second state we have. We have here 4 unpaired electrons are there in second state now. Now here, that is to say, in second excited state, this is a configuration you have in second state. 4 unpaired electrons are there. Now one more must be going towards this level, means we have like this now. There are now 6 unpaired electrons here, so it can form XeF6 molecule now. So this comes under third excited state. It is a second state we have. It is now coming under third excited state. In third excited state, we have 6 unpaired electrons are present. Therefore, it will be in third state for the formation of XeF6 molecule. sp3d3 hybridization. It has one lone pair on xenon present. So therefore, the structure is distorted octahedral structure we have because of the presence of one lone pair electrons on that. Now, xenon oxyfluorides. These xenon oxyfluorides, they are obtained by hydrolysis of xenon fluorides only. Xenon fluorides on hydrolysis will form xenon oxyfluorides or xenon oxides there now. So when you take hydrolysis of XeF4 and XeF6, with what it forms XeO3, xenon oxide is being formed. So XeF4 hydrolysis forms XeO3. Other products are xenon, oxygen gas and HF here. And then if you take XeF6 also, on complete hydrolysis of XeF6, you are going to get XeO3 and HF is being formed here. But when you take a partial hydrolysis, you are going to get oxyfluorides there now. So XeF6 on partial hydrolysis will form XeOF4, and on again further it reacts with water. The same XeOF4 further reacts with water and forms XeO2F2. So partial hydrolysis of the xenon hexafluoride is giving us XeOF4 and XeO2F2 here now. If xenon hexafluoride undergoes complete hydrolysis, we are going to get there XeO3 now. And during hydrolysis here, the oxidation number is not changing. Therefore, it is not a redox reaction. There is no change of oxidation state during hydrolysis. Hence, we can say They are not redox reactions. Let us now take the structures of the compounds. So XeO3. So in XeO3 again number of bonds, 3 bonds are there. We have 1 lone pair. Altogether 4 pairs are there. Hence it is coming under sp3 hybridization there now. So sp3 with lone pair, therefore structure is pyramidal shape we have. And it is colorless, explosive, and is coming under a third excited state now. If you see the molecule here, xenon is forming 3 double bonds are there now. 3 double bonds are there, xenon here. 3 double bonds means altogether there should be 6 unpaired electrons present. 6 unpaired electrons present. 6 unpaired electrons present is possible only in the third excited state. Already we have seen in the xenon fluorides there now. So it is 6 excited state here. So when you take the first excited state of xenon, it comes like this. The first state, excited state, we have 1 electron here and only 1 here now. The first state we have. If you go to second state here, means 1 electron gets excited there now. Then we have a configuration like this. So this will be second excited state we have now. And 1 more gets excited now. Then you are going to get 6 unpaired electrons now. Means 1 more going here. This is now third excited state. Third excited state we have now. So therefore it can form 6 bonds. In the 6 bonds here, 3 double bonds are being formed by xenon here. That is xenon here. We have 3 double bonds here now. And still we have 1 more lone pair is present on that. As regarding structure of xenon. So it is sp3 hybridization with 1 lone pair. So pyramidal structure we have. Next one is XeO4. We have altogether completely 4 bonds are there. No lone pair. So sp3 hybridization, tetrahedral structure we have. Colorless explosive solid. And comes towards it is a fourth excited state we have. Because previously we have seen in third state we have altogether there are 6 electrons here now. We require here 4 double bonds means 8 bonds we require. So we require 1 more excited state. Means here when you have seen in the third state we got this type of configuration there now. So 1 more must be excited here to this one. So that all will be unpaired electrons. Now this is taken as fourth excited state now. All 4 are unpaired electrons, hence it can form altogether 8 bonds are being formed by xenon. So we get like this. 8 bonds are being formed by that. So all these 8 unpaired electrons will form 8 bonds. There is a structure of xenon tetroxide we can say. Then XeOF4, xenon oxyfluoride here. So number of bond pairs and lone pairs here. So it is sp3d2 hybridization we have. Total number of bonds formed are here 5 altogether. Because 5 atoms are there here, means 5 bonds will be there. Still it has 1 more pair, so altogether 6 we have. 6 implies it should be sp3d2 hybridization now. And coming towards, it requires the total number of electrons 1, 2, 3, 4, 5, 6 are there. 6 unpaired is possible only in the third excited state we have. It comes in the third excited state then now. In second state, we have like this. Second state, it is having only 4 unpaired electrons now. We require 6 now. So therefore, 1 more electron must jump here now. So it is going to be now it is going to be now third excited state. Third excited state. Number of electrons are 6 in number. Therefore, it can form 6 bonds altogether. So 1 here, 2, 3, 4, 5 and 6 we have. Lone pairs is equal to 1 lone pair we have. Therefore, sp3d2 with 1 lone pair forms a square pyramidal structure. So it will be third excited state. Thank you.